Good evening, all of you. So, is it clear, audio and video? Okay, right. Okay. Uh, See, most of you getting one doubt in one of the question given in previous gate. So you don't worry about the questions, whatever making difficult to you. So just leave that type of question and proceed further. Don't waste any single minute also there. If it is not getting or there is any problem in the question, so just leave it because there may be in out of if you see the previous last 20 years papers, maybe some questions in for every 4 years or 5 years, one or two questions will be there that maybe data is wrong or they did not given properly that questions. Okay, so like that are there. So that type of question you just left and proceed further for with the remaining questions. Okay, so don't waste the time. And one of the question is given previously in the options. This is E1, E2, and flux. And current I1, I2 also in phase with this. And in the question they're given, I think that is a resistive load. Ideal transformer supplying resistive load. Then under load operation, the phasor diagram is dash. Okay, so they given like that. Now in that question, no option will satisfy first. No option will satisfy. Okay, because according to our definition point of view, if you think also EMF lags flux by 90 degrees, but they given in all options maybe lagging or leading like this, but EMF always lags only, correct, but here it looks like lead, but actually here minus E1 minus E2 should be there, then only it is correct. Because what is our actual phasor diagram? This is V1 flux, this is E1. E1, E2 always in phase, because the reason for EMF E1, E2 both flux only same. So both in phase. So this EMF is opposing the supply voltage. So generally how we represent in equation with minus sign we represent. Okay, EMF induced is minus V. So we represent with minus sign there. But magnitude of both E1 and V1 almost same. So if you put E1, E2 here, then it is also right. But here you have to take minus E1 minus E2 like this. Okay, you can put E1, E2 in downward direction, or you can take E1, E2 in upward direction, but you should write here minus E1 minus E2 opposite direction. It is actually E1, E2 is this, but you are drawing in upward direction, so that you have to take minus sign here, then it is also correct. Okay, but anyhow they did not given properly in any option, it is clearly. Okay, so leave this type of questions. This is right, option A is right in this, but minus E1 minus E2 should be there. Okay, in the last class we have completed the tests of transformer. Okay. Hmm. Current direction in phase, because if you remember ideal transformer case, generally we have seen in load operation, if the secondary power factor is UPF, what is the primary power factor? Little lags. But whenever no load current is neglected, when we neglect no load current, if it is given ideal case, ideal, no load current is what? Zero there. No load case, there is no current, ideal case. So when I0 is zero, I1 equal to I1 dash itself. Okay, that means if secondary is UPF, primary power factor also UPF. Okay, both are same. If secondary lagging, 0.8 lagging, primary also 0.8 lagging. So remember, whenever no load current is negligible or ideal transformer is given, then secondary power factor, primary power factor, both are same. That's why that I1, I2 are in phase here. Okay, same direction. Remaining test means that is I given just for to know what are the total tests. They are all manufacturing site tests we do, but not in our engineering level. Okay, so only that 4 tests we have in our syllabus for GATE and engineering services. What is there in option B? In option B, it is given flux. Okay, this is only no E1, E2. Okay, this is given I1, I2. But in option B, flux is leading. Flux is leading, and okay, you are considering directly EMF lags flux. Then that is also right. Okay, that is also correct. EMF lags flux by 90. But here it is not given first of all in the question properly, because what is this E1 here? Source or EMF induced. If EMF induced, they should take minus E1 minus E2. Okay, A is correct if you take minus E1 minus E2. Okay, and B also right here, EMF lags flux by 90. If you consider only the EMF induced without any supply voltages. So for such type of questions, we should not waste time, because no guarantee for this type of questions. Very rarely you will get. And very old question, that is also. Definitely it is not D. And they taken E2 in one direction, E1 in other direction. And there is no proper sign indication in this. Okay. Okay. So this is all unnecessary. So we proceed for the next topic. Now, previously we completed tests on transformers, polarity test, OC test, SC test, Sumner's test. Out of these 3, the most important for numerical point of view is only 2, OC test and short circuit test. And Sumner's test is only for theoretical type, and very rarely you will get question in GATE, but there is a chance to get in engineering service. Okay. Now let's see, after this tests on transformer, we have to see the performance of transformers. Performance parameters of transformer. Performance parameters of transformer. Now, to find the performance of any device, generally, what is the common parameter we use? Efficiency. And one more we use here, voltage regulation, because some voltage drop is there due to resistance and reactance of winding. Some voltage will drop regularly. So 2 parameters we will see in transformer. First one is efficiency of transformer, and second, voltage regulation of transformer. Voltage regulation of transformer. These 2 parameters. Efficiency in terms of losses we will calculate by using losses, and voltage regulation by voltage drop in the transformer, primary and secondary side. Now tell me one important objective question for PSU point of view. It is, in order to find efficiency, what are the tests you need to conduct? OC test, SC test, polarity test, both OC and SC test. What is the answer? In order to find efficiency, the tests required to conduct are dash. Yes, right. Yes, both OC and SC. Enough, enough. So both OC test and SC test we need to conduct. Okay, this is clear. Both OC and SC, because we need both iron loss and copper loss to find efficiency. Losses required for this. That is, we can find from OC and SC test. Similarly, to find regulation of transformer, what are the tests we need to conduct? OC test, SC test, polarity test, both OC and SC test. What is the answer? In order to find voltage regulation of transformer. Okay, okay, enough. Again, most of you saying OC and SC both, but the answer for this is only short circuit test. This is enough. only short circuit test we need to calculate. No need of OC test, because in short circuit test, if you remember, we have one objective, third one, to find percentage R, percentage X, and percentage Z. So these three are enough in order to find voltage regulation. So why it is in voltage regulation equation also you can observe we have only that percentage R, percentage X terms in the regulation equation. So to find that, if you know these three enough, no need to conduct OC test for this. For efficiency we need both tests, and for voltage regulation only short circuit test is enough. Okay, now tell me one more. In terms of efficiency, what should be the value to have good to say that it is a good transformer, good one? When we can say good? If you have high efficiency for every device or anything, when we can say it is good, efficient one, means high efficiency should be there. And in terms of voltage regulation, what should be the value so that transformer is good transformer? Low regulation or high regulation? Yes, the voltage regulation should be low. As much as possible, the voltage regulation should be low so that we can say it is good transformer. In efficiency should be high value. Best transformer is high efficiency transformer. Okay, let's see the first one. First, efficiency of transformer, right? First one, efficiency. See, these two topics are very important after iron losses. Iron loss, I said, the most important topic. In every examination, definitely we can expect one question from iron loss. Like that, after iron loss, the next important is performance parameters. So many times, engineering service or gate or any competitive examination, either on efficiency or on voltage regulation, or we have some questions combination, both efficiency and voltage regulation will come. Okay, so that type of questions, definitely from this topic we can expect one question for every examination, no doubt. And this numericals also easy one. Only the thing, you should know the concept very well behind this, so that each and every question you can solve. Right, first, efficiency of transformer. Efficiency. Now, what is the efficiency definition for anything, any device? How we find efficiency for any device? It is the ratio of output power to the input power. It is the ratio of output to input. That may be, if you any parameter you can take, output current by input current, efficiency, or output voltage by input voltage. But in transformer, we are finding directly power. So when you get some power from transformer, when you connect some load only, no? Suppose you are not connecting any load, then do you have any output power or any power drawn by transformer? Generally, it is drawing a small power under no load, that is equal to iron loss. That is very small. But in order to find the efficiency, we need to connect some load, and that load will have some power factor. Every load, whatever the loads you are connecting, that may have some power factor. So what is the efficiency definition now? It is the ratio of output power to the input power of transformer. What is both here? Electrical only. Output power also electrical, input power also electrical. But for rotating machines, if you go to generators or motors, output power, input power will be different. Suppose generator, what is the output of generator? Electrical power. And what is the input of generator? Mechanical power, turbine input. So mechanical output is electrical power output to the mechanical power input, if it is generator. Like that for motor also can define. But only in transformer, output is electrical, input also electrical. Now, which power it is? So we are saying output power by input power. Now, which power we have to write? We have active power, we have reactive power, we have apparent power. Now, which power we have to take? In the output power and input power, always in calculation, which power we need to take? PQS. PQS, which power we need to take? Yes, enough. Okay, yes, good. Most of you given right answer is active power. So we need to consider the active power output to the active power input, not volt ampere. This power we should not take, because maybe you people will get doubt now. So rating of transformer is in volt ampere, that is complex power or apparent power. Then why we are not taking that? Yes, rating of transformer is volt ampere, no doubt, volt ampere rating only, kVA rating power. But you are connecting some load, that load will have some power factor or not? Yes, definitely every load will have some power factor, cos phi, some power factor value, 0 to 1, some value will be there. Now when you substitute that power factor, now it will become V I volt ampere into cos phi. Then what is that overall power now? Active power. Even the rating of transformers are in volt ampere or complex power, the output and input power is always active power only. Okay, so write the definition first. It is the ratio of, it is the ratio of active power output, active power output to the active power input, active power output to the active power input. Okay, it is the ratio of active power output to the active power input at a specific power factor of load, at a specific power factor of load. Then if you write in equation form, efficiency equal to active power output to the active power input. Okay, then how can we write in equation form? It is, what is the output power? Simply we can write this output by output plus losses. So this input power we can also write as output plus losses. Okay, now output power, secondary side, the voltage current is secondary side, EMF or voltage is E2, current is I2, and power factor is cos phi, divided by output power E2 I2 cos phi plus losses. What are the main losses? Two, iron and copper. Iron loss plus copper loss. Copper loss is what? I square R. I2 square R02 you can write, or I1 square R01 also you can write. Both are same. But we are writing all the terms with respect to secondary side. That's why I'm writing I2 square R02. Okay. Copper loss. Iron loss plus copper loss. Now, one important observation here. How input is active power means primary voltage, primary current, and primary power factor is there or not. So in load operation we have seen everything. If there is some power factor of secondary, primary also having some power factor, then already we have seen, then primary also Vi cos phi is there or not? Yes. Okay, primary input also active power. Now one observation, so maybe you people now it doubt will not come, and after some time it So actually this is E2 EMF on secondary side and resistance R2, reactance X2, and this is the terminal voltage across the load V2. Okay, now we have to take this is secondary current I2 and load is having some power factor cos phi. So what is the output power of transformer means what we have to take generally V2 I2 cos phi we need to write. Okay, V2 I2 cos phi. But in our equation we are not writing V2, we are writing in place of that E2 I2 cos phi. Okay, why it is? Yes, why we are writing E2, why not V2? Because from the transformer data, we know about E1, E2 of transformer, but we don't have the idea of that V1, V2. V1, V2, we don't know. So because if E2 is 200 volts, what will be the V2 generally? Little less, based on the type of load you connected, you will get some 196 volts or 197 volts like that. Small little voltage drop, small 2-3 volts will drop, remaining voltage will go to load. Okay. So that small voltage drop we are neglecting because we don't know the exact value of that V2. So we will consider E2 itself in all our calculation. And one more advantage of writing that E2 is that E2 I2 will give directly the volt ampere rating of transformer. If you write that E and I, E2 I2, that is in place of that E2 I2, you can take volt ampere rating. Suppose there is a 10 kVA transformer given. In place of that E2 I2, you can write 10 into 10 cube directly and some power factor, whatever they given in the question. Okay, so we are not writing V2. In place of that, we are writing E2. That's why I written this one. Therefore, this equation is nothing but efficiency of transformer at full load condition. Full load. What is full load means? The corresponding current in the equation is full load current. So what is the current here? I2. That I2 we call full load current. How to find full load current? Many times I given. Suppose there is a rating 10 kVA and voltage rating 400 by 200. How to find full load currents on any side, primary or secondary? If you want to find secondary side full load current, I2 equal to, how to find? Use the kVA rating 10 into 10 cube by 200. So calculate this 50 amperes. Okay, that is the full load current of secondary. That current we call full load current. So accordingly, we are writing here the equation. Efficiency at full load is E2 I2 cos phi divided by E2 I2 cos phi plus iron loss will never change. Whatever the load, iron loss fixed, constant it is. Only when voltage changes, then only iron loss will change. But we are not changing any voltage in transformers fixed. So iron loss is a constant loss. And copper loss is full load copper loss. So that is I2 square R02 full load copper loss. Or write directly I2 square R02 only. I2 square R02. So this is the formula for efficiency at full load condition. Full load condition. Now, suppose we need to find efficiency of transformer at half full load condition, because there is a transformer of 10 kVA rating, for example. Is the transformer always supply 10 kVA? No. The transformer may supply 1 kVA and it may supply 3 kVA or it may supply 6 kVA. Like that, any power or any load it can supply. Up to what it can supply? Up to 10 kVA it can supply. Whenever it is supplying 10 kVA, then we call the transformer is under full load condition. Okay, like the transformer may supply 1, 2, 3, 4, 5, 6, up to 10 it can supply. Any load it can supply. That depends on you are connecting. You are only connecting load, no? So we are connecting load to transformer. You can connect any load up to its capacity. That you should take care. Otherwise, if you connect beyond its capacity, it may become overload, overheated, and if the heat crosses the limit of the range, whatever we fix, and then it may damage the copper windings. Okay. Now, efficiency at half full load. Efficiency at half full load. Like that, anywhere you can write 3/4 full load or 70% or 80% like this. Suppose efficiency at half full load required. Efficiency at half full load. Then Same equation, what will change? E2 will not change. Only current will change. Currents will change. Now in place of that current, take I2 by 2, half. E2 remains same. Voltage will not change. Current become half. Power factor also we are not changing. Fixed. E2, I2 by 2, cos phi. Iron loss always constant, any load condition. And I2 by 2 whole square. I2 by 2 whole square into R0 2. Okay. Now if you simplify this, efficiency at half full load condition. Efficiency at half full load condition equal to that 1 by 2 I'm writing outside. 1 by 2 into E2 I2 cos phi divided by 1 by 2 E2 I2 cos phi plus that 1 by 2 whole square na it is. So 1 by 4 will come, that is I'm writing outside, and remaining is I2 square R02. What is I2 square R02 means? Full load copper loss na it is. See, previously we taken I2 square R02, nothing but full load copper loss. I2 square R02 is nothing but full load copper loss. Okay. Now therefore, like this for any fraction of load, now we can generalize this for any type of loads using one fraction. Therefore, at any fraction of load, at any fraction of load, x full load. So we call x full load, any fraction. Half full load means x is 1 by 2. 3/4 means 3 by 4 times of full load. Or 70% means what is x value? 0.7. Or 80% means 0.8, and so on. So where x is the fraction of full load. X is fraction of full load. That is 0 to 1, it will change. Then what is the formula in general? Therefore, efficiency at any fraction of full load, x full load, we write generalized. Same above equation we are generalizing. See, 1 by 2, 1 by 2, 1 by 2 here. So x full load means x into E2 I2 cos phi divided by x into E2 I2 cos phi plus iron loss will never change. That is always constant. It is independent of your load. And 1 by 4 is there. 1 by 2 means 1 by 4 we got. So x means what we get here? X square into full load copper loss. Remember this equation. So this is the generalized equation for efficiency. Okay. Generalized efficiency at any fraction of load. If you remember this enough, most of the problems. And one more equation I will write. Same equation, little modification. That is, in place of this E2 I2, voltage current product, I will write volt ampere rating of transformer. That's it. Okay. So same equation I'm writing again. Why we are not considering other two losses? What are the other two losses? Okay, the other two losses are stray load loss and dielectric loss. So I already given a statement. These two are the minor losses. We never use the two losses in our calculation. We will neglect that losses. Main losses are iron and copper only. Iron losses is not neglected. Iron loss is there na here. Okay, here I did not return. Okay, by mistake I forgot. Here iron loss is there. Okay, iron loss is there, was missed, plus 1 by 4 I2 square R02. Okay, iron loss is there. See, Strava, again you are getting doubt. As I changes, E should change. So I given many times this statement, whatever the load variation, voltages in the winding will never change because constant flux device, EMF in windings never change. Only current variation. Only current variation. Load variation is current variation only. And load power factor also sometimes will change. But the voltages in the windings will never change. They are fixed. Yes, HPCL accident occurred. Just now it is fire accident. That is also asking to me why HPCL. Okay, so same equation I'm little changing with respect to volt ampere. See, the same equation, efficiency at X full load. What is X? Fraction it is. If they 70% at find the efficiency at 70% full load, means X is 0.7, or find the efficiency at half full load, then what is X? 0.5. Okay, this is equal to X into volt ampere cos phi divided by X into volt ampere cos phi plus iron loss plus X square copper loss. So this copper loss is full load copper loss. See, 99% for every question, whatever we will solve now, we will use this equation only. Okay. This equation we will use in all numericals. Volt ampere, that is the rating of transformer given in the question. VA. So this WCU means full load copper loss, that is. So every time we no need to write FLCU, full load copper loss. Copper loss means full load copper loss in the equation always. X square full load copper loss. Okay. Shiva, just now I said about that. Whenever load is changing, EMF in windings will not change. Why? That is also given. No, it is a constant flux device. Flux same in the core. So EMF will never change. Only current variation will be there when load is changing. EMF will never change in the transformer winding. That is always constant, fixed. Up to you don't change the supply voltage, EMF in windings also fixed. Okay. Now, according to this efficiency, we need maximum or highest efficiency required for us. So efficiency what we require, high efficiency required, so that transformer we can say good one. Now, in order to have maximum efficiency of transformer, what are the conditions? That conditions we need to calculate so that we will operate the transformers nearly at that conditions. Then we get maximum efficiencies of transformer. So, right, setting condition for maximum efficiency. Conditions, we have two conditions for maximum efficiency. Conditions for maximum efficiency. So why two conditions is, observe this equation. Two conditions generally you should know very well from mathematical point of view, mass. If there is any function, how to find the maximum value of that function? Tell the procedure. Differentiate that function with a variable and equating to 0. Then we get condition from that. And that condition we will substitute in the same equation again so that we get maximum value. Okay, that is the procedure to find condition for maximum value. Now, in the same way here, we will differentiate this efficiency and equating to 0. We get one condition. And that condition we utilize so that we get maximum efficiency of transformers. Now, tell me in the equation first, how many variables we have? Maximum values always depends on variables. What are the variables in this equation? Yes, one variable is current. Current will change when load is changing. Okay. And one more variable is what? Power factor. Because power factor of load is not same. One load is having UPF, one load 0.8 lagging, other load 0.7 lagging, different load power factors. So the range of power factor is 0 to 1. But in practical, mostly the power factor of loads, whatever we are operating, the motors, loads, all will be in the range 0.7 to 0.9. In this range, we operate the loads. Whatever the loads we have, they will operate in this range, 0.7 to 0.9. So how many variables total? Two variables. If you change current from 0 to its full load, at one of the current, you will get maximum efficiency. Like that, if you change power factor from 0 to 1, at one of the power factor, you will get maximum efficiency. So we have two variations: load current variation, load power factor variation. Based on the two conditions, you will get. Yes, right. We have two conditions. One is load current variation. Load current variation. Second, load power factor variation. Load power factor variation. First condition, second condition. With respect to load current, with respect to load power factor. Now let's see what are the conditions from these two. Right, the first one, load current variation. First one, load current variation. So you can change load. Suppose 10 kVA transformer, you can connect from 1 kVA to 10 kVA. But where transformer will give maximum efficiency? At one particular load, when you operate, it will give maximum efficiency. Now, what is that load or current? That is we need to calculate. So that is called load current variation. Now, what is the procedure for this? Differentiate. See, for maximum efficiency, differentiate the efficiency with respect to load current. Now there are two variables, current and power factor. So when you change one variable, the other variable you should keep constant. Don't change power factor now, only current magnitude and equating to 0. Okay, differentiation with respect to current by keeping power factor value constant and equating to 0. So condition we are using, condition applied. Condition is what? Differentiate the function with a variable and equating to 0. Then we get one condition from this equation. Now, which equation you have to differentiate? This one. In terms of current, what? This is the equation. X e to I2 cos phi by this one. Differentiate this equation. Okay. Then the final answer I'm writing. And what is the form of this differentiation? Numerator, denominator, both having I2. So u by v differentiation. No, u by v differentiation. What is the u by v differentiation? V dash u minus u dash v by v square. Okay, so use this formula and equate this is to 0. But I'm not doing this completely now. For gate examination point of view or prelims objective point of view, no one will ask you. Only in the mains examination. So those whoever will qualify prelims, again, those whoever is taking for ESC, in the mains examination, I will discuss again all this in detail. All derivations, whatever is required, because this conditions is important there in conventional type of examination. Particularly they will ask, explain the procedure or what is the condition for maximum efficiency with respect to load variation. Then you have to derive this complete equation. But anyhow, I'm not deriving completely, so I will write directly. Use the differentiation formula, and finally you get the condition is x square I2 square R02 equal to iron loss. So this condition you will get. If you differentiate, you will get this condition. Now from this, if I rewrite x square, what is I2 square R02 means? Full load copper loss. Full load copper loss. This is equal to iron loss. Now, if you find the value of x, Or simply, if you take this equation, first one, tell me here, from here, what is this means in theoretical? This is a copper loss or not? This left hand side term is what? Copper loss. I2 square R0 to X square. X square means fraction. This is the copper loss at some load equal to iron loss, or simply copper loss equal to iron loss. Copper loss equal to iron loss. This is the condition for maximum efficiency. Copper loss should be equal to iron loss, or variable loss should be equal to constant loss. And many people will get confused here. Sir, iron loss equal to copper loss or copper loss equal to iron loss? Statement wise, both are same. Both are same. But which one to be replaced? Tell me. Iron loss will change? Never. Copper loss only changing. That copper loss you should equate with iron loss. Or simply remember this. At maximum efficiency, total loss of transformer is 2Wi. Okay, remember this enough. Total loss means actual iron plus copper, total loss in transformer. But at maximum efficiency, what should be the copper loss? It should be equal to iron loss. So iron already there, and copper loss also equal to iron loss. Then total 2W. Okay, copper loss should be replaced with iron loss. But don't replace iron loss with copper loss. Iron loss will not change. That is fixed one. So this is the condition for maximum efficiency. Copper loss must be equal to iron loss. And if you write completely, where we get maximum efficiency is X. X equal to square root iron loss by full load copper loss. The most important, many times in many examinations, GATE, ESC or PSUs, anywhere, this is only the equation we are getting questions for 1 mark. For 2 marks, you will get little calculation of efficiency that we will see. This is very important. At what is X means? X is what? Just now we have seen X. It is fraction of load. Fraction of full load where maximum efficiency occurs. Where maximum efficiency occurs. Okay. So we don't know where we get maximum. Suppose there is a 10 kVA transformer I given. It can supply 1, 2, 3, 4 up to 10. Now at what kVA it will give maximum? 70% or 80% or 75 or 85. So that 80% of load, this is X. If you know iron loss of transformer and full load copper loss of transformer, use this equation, you will get a percentage of load where the transformer efficiency is maximum. Okay, clear all of you? This is first condition. With the load current variation, it is with the load current variation. Yes, condition for maximum efficiency theoretically is what? Copper loss equal to iron loss, or variable loss equal to constant loss. Or if they ask particularly at what fraction it is maximum, then use X. Okay, this is one condition. One condition in terms of current or load magnitude it is. Now one more condition we have with respect to power factor variation. Before that, I will give the graph of this, how efficiency will change with current. Observe carefully. See, efficiency versus current variation, load current. Now whenever if current is zero, when secondary current is zero, tell. Secondary current zero whenever open circuit means load is not connected. Then I2 0 means what is output power? Zero. Then efficiency also zero. So when I2 0, efficiency also zero. Now whenever I2 increase means output power increasing, so efficiency also increases. So whenever current increase, efficiency increase, current increase, efficiency increase, and reaches maximum after that slight decrease in efficiency. Okay, this is the variation of efficiency. So let us consider this is the full load point, full load current it is, and this is the no load, zero current. No load means current zero, and this is maximum efficiency, maximum, and at this particular current we are getting maximum efficiency at this particular current. And what is the condition here? We got copper loss equals to iron loss. See, full load means what? Suppose with a example just now previously given 10 kVA 400 by 200, what is the current I2 we got? 50. Now full load means 50 amperes, half full load means 25 amperes. Like that, at one of the current here you are getting maximum efficiency. What is the condition at that time? Copper loss equal to iron loss. But before reaching that maximum efficiency in this range from no load to this point, what is the relation between copper loss and iron loss here? Which one is greater? Iron loss never change. Whenever current increasing, copper loss also increasing. At this current both equal. So before that, what happens now? Copper loss is less than iron loss. Okay, because current is less, so copper loss is less. At this current both equal, copper loss equal to iron loss. Now after reaching maximum efficiency, after that maximum efficiency, if further load increase, current increase, whenever current increasing, copper loss still increases, so you will get copper loss is greater than iron loss. Okay, remember that relations. Before reaching maximum efficiency of transformer, which loss is greater in transformer? Iron loss is greater. And after maximum efficiency condition, copper loss will be greater than iron loss. Clear all of you? Okay. So this is the variation of efficiency with current variation or load variation, we call it is. See, don't confuse in this equation. Copper loss equal to iron loss means x equal to not 1. X is not 1. This is not at full load. X is some fraction. Copper loss, if you see the questions, you will understand. Copper loss equal to iron loss means don't say x equal to 1. So I am see, I written here directly. I am saying that here is x equal to 1. No, this is the copper loss at some fraction. At some fraction, not full load copper loss. Copper loss, theoretical statement, copper loss equals to iron loss. That's it. But don't say that x equal to 1 there. Both equal. So this is the copper loss at some fraction combinedly. I2 square R02 only full load copper loss. And x square is multiplied here. So this is copper loss at some fraction of load. Sunil, I am not visible. Check from your side only, that is. Next, second condition. First condition we have seen load current variation. Now let's see the second, load power factor variation. See, every device will give maximum efficiency at some particular point. Suppose take motorcycle. So is the motorcycle will give good efficiency like mileage, good mileage, whatever the speed you will drive? No. If you drive in economic region, like 30 to 50 kilometers per hour approximately, then you will get good mileage, maximum efficiency of that motorcycle. But if you drive at 80 kilometers per hour or 100 kilometers per hour or 20 kilometers per hour, do you get high efficiency? No, mileage will be reduced. In the same way, transformer also, rating of transformer 10 kVA, but this transformer will not give same efficiency for whatever the load you are connecting. It will give high efficiency only when it operates almost 70 to 80, 70 to 90% approximately in this range. If you operate in this range, means 7 kVA, 8 kVA, 9 kVA, in that range, it will give maximum efficiency. But at this is no load. See, at this current, for example, here, what is the efficiency of transformer? Very less. Like that, if you are operating little higher currents or little high loads, then it will give maximum efficiency, nearly that full load condition. And after that, slightly again efficiency reduce. Why? Current still increasing, no? Then I square R still increase. That's why little efficiency drop here. Okay, second variation. Second, load power factor variation. Load power factor variation. See, after listening the theory concept, if you see questions, then only the confidence will build. Theory only not important. Suppose you learn theory very well, but you are not solving any one question, then no doubt you cannot solve any question further in any examination. Because after listening theory, if you are able to understand the question or able to do some numericals, then only your confidence will build. So hope most of you may do now well after listening some concepts. Like that, after completion of some more topics, I am sure that you go back to the previous topic, then easily you will understand each and every question. But you should practice. You should practice by just listening or by just saving your PDF notes is not at all will give any subject to you. Okay, everyone will have PDFs will be there and number of questions will be there, textbooks will be there. But what is the use of that? Try to solve. That's why I'm solving many questions in the class itself. As much as possible, everyone try to solve in the class itself. Don't take just the solutions. You solve here itself, because no doubt after this you cannot practice anywhere again. Definitely you don't practice. That much time you don't have. So practice as much as possible right now itself. Yes. Next, load power factor variation. Again, same procedure. For maximum efficiency, apply the condition. Differentiating efficiency with respect to power factor variation. So with respect to d phi, we differentiate power factor angle. Cos phi is the power factor. Okay. Then in that mainly phi is changing. Power factor angle will change. So power factor will change. So with respect to phi, we are differentiating and equating to 0. Now, if you observe the equation, both the numerator, denominator, both having phi, cos phi. So it is also same form of differentiation, u by v form of differentiation. So again, if you differentiate, we get one condition. So finally, the condition I'm writing, that is cos phi equals to 1. You will get this condition. Cos phi equal to 1 means at which power factor you are getting UPF? At which power factor you are getting maximum efficiency? Unity power factor. Cos phi equal to 1 means what? UPF. Unity power factor. So at UPF, the efficiency of transformer is maximum. At UPF only we get maximum efficiency. You should know this condition to solve some of the numericals. If you don't know this condition, there you will get doubt. What power factor I have to take? So there UPF you have to take whenever they ask to find maximum efficiency. Now the load variation, efficiency variation is like this. Take the graph. Efficiency, current only. And what is the condition in this case? You need to keep I2 constant. Magnitude of current you should keep constant now. Power factor only you are changing. How power factor you can change? Take different load, R load, RL, different types of combination, or just L added, little more inductance added. So RL. So in RL combination, you will get 0.9 or 0.8, 0.85, 0.86, 0.88, like the different types of power factors. Then when you are changing load power factor, your maximum value of efficiency will change. See, it will be like this. This is the efficiency variation, same as previous graph. Suppose we got it is for 0.4 power factor. Okay, same as previous graph, but it is at 1 power factor we are drawing. Like that, if you change the power factor to 0.6, little efficiency increase. This is for 0.6. Like that, if you take some other 0.8, we get like this 0.8 power factor. And for UPF, you will get maximum efficiency. This is UPF 1. For different power factors, when we are drawing, the highest or maximum efficiency is given by UPF load. Same current, see, for the same current we are considering. Same current, the maximum value is different for different power factors. And where it is maximum? For UPF only, it is maximum. Okay. Yes. Yes, maximum efficiency means that condition is their copper loss equal to iron loss only. Yes, enough. Okay, so these are the two conditions where the efficiency of transformer is maximum. One condition is what? With respect to current, that is copper loss equal to iron loss, their efficiency is maximum. And second condition is at UPF, you will get maximum efficiency. Okay. See, if you take at any current, suppose take here, for this current I2, if you draw efficiency for different power factors, where we get maximum efficiency, UPF only we get. So maximum is not the peak of every time. For every current, if you consider anywhere here, the maximum value we are getting for UPF only. Highest value we are getting for UPF only. Okay. If you want maximum efficiency, you have to take UPF, and you have to also take previous condition, copper loss equal to iron loss. Then this point you will get maximum efficiency. Okay. Yes, good. Now I am coming to that point only. Yes, both conditions, if you apply, maximum is possible. If you apply any one, current may not be at proper value. So if you take different currents, suppose 0 to 10 amps, 10 amps is the full load. If you take 4 ampere, that current is not giving maximum, not directly, because 4 means 40% only. Nearly 70 to 90% when you operate, you may get maximum efficiency. So in numericals, you will understand all this. Now, make a note. Make a note. Make a note. At what kVA transformer efficiency is maximum? Suppose the rating of transformer is given, rating equal to 10 kVA. Now at what kVA transformer efficiency is maximum? So this question or this point they may ask sometime, at what load kVA transformer will give maximum efficiency? Suppose you need to connect load, and that load we should consider such that within the range of transformer. Suppose 10 kVA is the rating of transformer, and what is the load you need to take? Can you take more than 10? No, we should not take. So you have to take a load in between 1 to 10. Up to 10 you can apply. Like that, at what load kVA if you connect transformer will give maximum efficiency? So that we need to calculate. So write that point. The load kVA of transformer, the load kVA at which the load kVA at which the efficiency of transformer, the efficiency of transformer is maximum is you simply multiply the kVA rating of transformer with x into full load kVA, x into full load kVA. So use this equation. Why? Because volt ampere rating of transformer is what? E to I2 only, no? Volt ampere rating of transformer is E to I2. Now I2 means actually full load. Then where we are getting maximum efficiency? At some fraction. So in place of that I2, you have to take E2 is never change. In place of I2, write xI2. Because at some fraction, 70% or 80% or 85%, you will get maximum efficiency. So in place of that I2, I'm writing xI2. How to find that x? We have the formula. What is x? Square root iron loss by full load copper loss. Just now we have seen. Now find this value of x here and substitute here, you will get that value. So that is x into E to I2. E to I2 means what? Full load kVA. Whatever given on the nameplate, that is itself full load kVA. Now substitute that is here. Full load kVA of transformer. Okay. If they ask at what kVA transformer will give maximum efficiency, then just multiply the full load kVA of transformer by x. Okay. Let's see some numericals on this so that some more clarity will get on this efficiency. Completed. See the question. See this question. A 4 kVA transformer has iron loss of 200 watts and full load copper loss of 200 watts. The maximum efficiency at unity power factor is dash. So we need to find maximum efficiency at UPF. So maximum efficiency is possible with two conditions. One condition is what? With the load current variation. Then for that we need to use first condition. What is the first condition? X equal to square root iron loss by full load copper loss. Now you will get x value here. That x you need to substitute in equation. And the second condition is what? The efficiency maximum is possible at unity power factor. But anyhow, they asked in the question UPF. But sometimes in some of the questions, they don't give this UPF. They will ask what is the maximum efficiency will be dash. That is itself question. The maximum efficiency is dash. then what you will take power factor in the equation? UPF you have to take, because there only we get maximum, no? And first condition you should apply. Now using these two conditions, we have to solve. First solve x square root. What is iron loss? 200. And full load copper loss directly they given here. So 200. Then what is this? 1. X equal to 1 means full load only. Full load only. X equal to 1 means full load. Now UPF. Therefore, maximum or efficiency formula is what? Efficiency XFL equal to X into volt ampere cos phi. So write the formula for 2-3 times at least. Don't write directly. X volt ampere cos phi, X volt ampere cos phi plus iron loss plus X square full load copper loss. This is the formula for efficiency. Now we need maximum. So two conditions we are applying, first and second. X equal to 1. So 1 volt ampere. What is the volt ampere? 4 kVA given in the question. 4 into 10 cube. At UPF directly they given. Suppose sometimes they will give find the maximum efficiency at 0.8 lagging. Sometimes they give 0.8 lag also. Then you have to take 0.8 only. If nothing is given in the question, then you have to take UPF. Anyhow, UPF they're given directly here. 1. 1 into 4 into 10 cube into 1. Iron loss 200. X square is 1 square only. Full load copper loss is 200. Calculate this into 100. Find how much? Yes. 90.9, right. The answer is 90.9 percentage. So that is the maximum efficiency of transformer, 90.9 percentage. So the only device in electrical machines is transformers to have a efficiency of more than 90%. But remaining induction motors, DC motors, synchronous machines, if you go, you will get 60 to 80% mostly. Okay. And induction motor little higher, like 85 also possible. And DC and synchronous, very less power factor, very less efficiency. Jadhav, 4 kVA, what is the rating indicates here? Is it input or output? Both. The rating, kVA rating given in transformer, same for both primary and secondary. It is not input, it is not output. That is same for both primary and secondary side. So directly whatever volt ampere given, substitute here. That's it. Percentage, no. Don't multiply. If you don't multiply with 100, what you will get? Check 0.909 you will get. Okay, next question. Next question. See this question. A single phase transformer has no load loss. No load loss means iron loss. 64 watts. This is 2 marks. This question 2 marks, but solution is just 30 seconds, not more than that. Okay. When a short circuit test is performed with 90% of rated currents flowing in both the LV and HP, only 90% current is flowing, not rated current. Then what is the measured loss? In short circuit test, whatever loss you got, that is copper loss. So what is the copper loss given? 81 watts. And this copper loss is at full load? No, this is not at rated. This is at 90% of rated. That is given clearly in the question. Now we have to find the transformer has maximum efficiency when operated at dash. At which percentage of current, if you operate, maximum efficiency transformer will give. Try this. What is the answer? Tell me. Just 30 seconds, not more than that. Hmm. Maybe there is chance to do by mistake some other answer also you may get. Take care of that. Yes, some of you getting 88 percentage. Check that once. Check that once. Because what we have to find here, percentage of load or fraction of load. Percentage of load or fraction of load, both are same. Fraction of load. Fraction of load at maximum efficiency. That is what X. X we need to calculate. What is the formula for X? Root iron loss by full load copper loss. By mistake also don't write iron loss by copper loss. Definitely you will get wrong. Don't write by mistake this X here, iron loss by copper loss. Full load copper loss only correct. But given in the question given the copper loss is 81, that is at 90%, not at full load. Not at full load. So first you calculate what is the full load copper loss. How to find? See, copper loss is 81 watts. This is at what percentage? 90%, means 0.9. At 0.9 or 90 percentage, it is 81. Now what is the copper loss at 100% or full load? Full load means X equal to 1. Then what is the formula? Or if you don't know formula also, copper loss proportional to square of current. So copper loss in case 2 by copper loss in case 1 proportional to square of that percentage, 1 square by 0.9 square. So calculate copper loss in second case, 81, 1 by 0.9 whole square means 0.81. How much it is? 100. Okay, this is the full load copper loss. 100 watts is the full load copper loss. Now substitute in the X, square root. Iron loss will never change, directly you can substitute 64 divided by 100. Now what is this? 0.8. So the percentage of load at maximum efficiency is 0.8, means 0.8 fraction. Percentage means multiply with 100, then the percentage of X, a percentage of load, is 80 percentage. Okay, answer is C. And some of you got 88, that is because directly you substituted 81. That's why they given in the option also, that is. Okay, next question. Completed this. Read this question. A 500 kVA transformer has constant losses of 500 watts and copper losses at full load are 2000 watts. Then at what load is the efficiency maximum? 500 kVA means full load kVA it is. But it won't give maximum always at 500. Definitely less than that. Not at very low. Now that we have to find. Just now I given one equation. The load kVA at maximum efficiency. Load kVA at maximum efficiency. What is the formula given? X into full load kVA. What is the full load kVA? 500 here. So you need to find X in this. Only X you need to calculate. What is the formula for X? Square root iron loss by full load copper loss. Direct substitution. Iron loss is 500. Copper loss is 2000. So 1 by 4. So 1 by 2. 1 by X is 1 by 2. Means 50 percentage. So 1 by 2 into 500 kVA. The answer is 250 kVA. Yes, right. Okay, at 250 kVA, this transformer will give maximum efficiency. Okay, clear all of you this? 1 by 4, root of 1 by 4, nothing but 1 by 2 only, no? Next question. Yes, sir. Rated kVA is full load kVA only. Rated or full load both are same. Simple. See this question. A 500 kVA transformer has efficiency of, so all of you completed previous one. Jayanta. How 1 square by 0.9 square? How it is written? Copper loss proportional to square of current. Square of current. 90% means 90% current means 0.9. Full load means 100% means full load. That is 1. So second case now it is copper loss at full load is copper loss 2. Nothing but proportional to 1 square. So this is copper loss 1 means 90%. Square of currents I written 1 square by 0.9 square percentages. Okay. A 500 kVA transformer has efficiency of 95% at full load and also at 60% full load. So listen carefully this. Both at UPF. Both at UPF. The efficiency of the transformer at 3/4 full load will be dash. So we need to find finally efficiency at 3/4 full load. Means X is 3 by 4. First of all, write the formula one time. What is the efficiency at any fraction X full load? Formula. First write that. X into volt ampere cos phi divided by X into volt ampere cos phi plus iron loss plus X square full load copper loss. Okay, this is. Now we need to find efficiency at 3 by 4 means X equal to 3 by 4. This is clear. Now at what power factor we need to find? That is also required now. X is 3 by 4. Volt ampere is there in the question 500. But cos phi they did not mention. So we will assume cos phi is 1 because already they given 95% at full load, 60% at half full load it is. See, both are having same. This is 60% at half full load. It was missed. 60%. Okay, not 60%. See, listen carefully. It is having efficiency of 95% at full load and also at 60% of full load. Understanding question itself important. Both at UPF. But in the question, they did not given iron loss. They did not given iron loss. And they did not given any copper loss. Both unknown for us. To find the iron and copper loss both, they given two conditions. What they given? They given efficiency at full load given. Full load UPF is how much? 95%, and also at 60% of full load. 60% of full load means X is how much? 0.6. So and also at 60% UPF, both at UPF, same efficiency, 95%. Okay, full load means X is 1 here. 60% means X is 0.6 here. UPF both. Now apply the same formula for the given two conditions. Apply the same formula. Then calculate iron and copper loss from the two equations. Okay. So this is a given statement. Efficiency at full load UPF 95%. Efficiency at 60% of full load UPF also 95%. Is it possible? First, same efficiency at two different loads, full load and 60% of full load? Yes, possible. How it is? Observe the figure previously we drawn. Observe this. This is full load point. Assume that this is full load. Now, here and here, same efficiency are there or not? Observe. At this point and this point, same efficiency. And this is full load current. And what is this current? This is not full load. Let's consider this is some 60% of full load. According to given question, I'm saying this is 60%. This is full load. At both cases, same efficiency 95%. Now, where we need to find efficiency? We need to find efficiency 3/4. Where is 3/4 now? 3/4 means what? 75%. 75 means somewhere here. So like that, here you will get some more than that 95%. You will get a efficiency at 3/4 full load is more than 95%. Okay. So definitely 87 you can strike out. 92 also you can strike out. 95 also you can strike out. Answer is 98. The question is very big, but you no need to solve in the question in the examination if you have a proper idea on the question. Okay, so try to solve this question, check and how much you are getting. See, according to given data, so I'm writing the equations, efficiency equation. Observe, efficiency at full load UPF is 95%. So I'm applying the efficiency equation to this. Full load means X is 1 volt ampere given 500 kVA, UPF 1. So 500 into 10 cube direct I'm writing, plus iron loss X square means 1 square only, full load copper loss. This is equal to 0.95. Okay. Now cross multiply and you will get one equation in terms of iron loss plus copper loss, some value. Let it is equation 1. In the same way, efficiency at 60% given. Efficiency at 60% UPF is same 95%. That is 1 into X is 0.6. X is 0.6. Same kVA, 500 into 10 cube. This is also at UPF divided by 0.6 into 510 cube plus iron loss X square means 0.6 square. X is 0.6 square into copper loss. This is equal to 0.95. 0.95. Now again cross multiply iron loss plus 0.6 square copper loss. You will get one equation. Let it is equation 2. Two equations. There are two unknowns in this. So you need to solve by calculator. So by solving the above two equations, by solving 1 and 2, you will get iron loss and copper loss. Tell what is the values of this? What is iron and copper? Iron loss how much? Aishwarya, copper loss 16,447. Iron loss 9868. Okay. Copper loss 16447. Is it right? Check all of you this. So you have to tell the answers. Okay, little variation, no problem, because by taking that 0.6 or like that, you will get some small variation. Anyhow, approximately copper loss is same. Okay, good. 16.448. 9.86 kilowatts. 16.448 kilowatts. Okay, right. So this is iron loss. This is full load copper loss. You will get from the question. Now, once you know iron and copper loss, now you can find efficiency at any fraction of load. Now, therefore, we need to find at 3 by 4. No, therefore, efficiency at 3 by 4 full load. Power factor they did not given in the question. So we are taking the same power factor, whatever they given previously, UPF. So X is 3 by 4 into 500 into 10 cube into power factor is 1 divided by 3 by 4 500 into 10 cube plus iron loss we calculated now 9868 watts and copper loss x square copper loss x square is what 9 by 16 into copper loss 16447 watts into 100. So approximately you will get 98 percentage. It is check this value 98 percentage. Calculation important. If you want to solve this question in examination, it will consume nearly 2 to 3 minutes or 5 minutes also. But if you have little concept, no need to solve this question in examination. Even calculator is required. Without that, we cannot solve. But still, you can solve just by observing options. Okay, all of you got same 98 percentage. Nearly 98 percentage. Or how much it is? What is answer? What is the answer? Maybe exactly not 98, 98 or 95. Check. How much? Pragati, how much? 95.14. Check 95 or 98. 95 or 98. Some of you getting 97. Okay, all of you getting 95.15. Okay, right. Not 98. 95.15. Most of you getting same. 95.15 percentage. So almost it is not 98. 95 percentage only. 95.15 you are getting, no? 95 percentage only the correct. But exactly they given 95, but not exactly 95. Little increase. Why little increase? Observe that variation in the graph. Observe the variation. The transformer is having same efficiency 95 percentage at full load. See, this is efficiency and current variation. Assume that this is full load current. Okay, full load current, and they given same efficiency at a 90 at a 100% or full load condition and at 60%. Let us consider this is 60 percentage. This is full load and both efficiency 95 percentage. Now where we need to find efficiency? We need to find efficiency at 3 by 4. 3 by 4 means 75 percentage somewhere here. This is 3 by 4 or 75 percentage. Then if you find efficiency here, definitely it will little increase than 95 percentage. But depends on numerical. Sometimes you will get so much variation like 98. I said I assume that 98, but almost in this question you are getting little near to that 95 only. Little increases, but in the option still they given 95 only. Okay, either 95 or 98. but depends on the question. You have to consider whether it is 98% or 95%. So here you are getting exact answer is 95.15%. Most of you given this answer. Okay, but in the options we don't have this 95% only there. That's why answer is 95% only. Okay, so like this you can answer if slight variations are there. Yes, 95.14 or 15, that is only correct. Okay, right. Next, one more question. Next question. Just you should know how to solve this question, this type of question. Okay. Sometimes they don't give this iron and copper loss. You need to calculate iron and copper loss by solving the two cases. If full load case and 60% case, using that iron and copper loss is calculated. Okay. Next question. This is one model from test data. It is open circuit test and short circuit test. This is from short circuit and open circuit test data. Read the question. A 4 kVA 200 by 400 volt 50 hertz single phase transformer has the following test data, not test figures, test data, that is no load test means OC test and short circuit test. So no load test data. In OC test we have three readings: voltage reading, current reading and watt meter reading. They given. And short circuit test also three readings: voltage, current and power. 9 volts, 6 ampere, 21.6 watts. Okay, the data given. Now we have to find efficiency of transformer on full load at UPF. Use the same formula. What is the formula? Write it first. Efficiency at any fraction XFL equal to X volt ampere cos phi divided by X volt ampere cos phi plus iron loss plus X square copper loss, full load copper loss. Now in the equation, what is unknown for us? Volt ampere rating is there, 4 kVA. X also they mentioned, where we need to find efficiency, full load. So X equal to 1, and UPF also they given, power factor. Iron and copper loss we can observe from OC and SC test. OC test will give iron loss, short circuit test will give copper loss. But blindly don't substitute the given test data directly in equation. That is iron loss, no doubt. This is copper loss, no doubt. But don't substitute directly. Let us check one time. What we need to check is OC test. Where we conduct OC test always? Rated voltage. Now OC test is always LV side. Check LV side rated voltage. This is LV, this is HV. So LV side 200, so 200 only. So this is correct. Iron loss is correct only. But check short circuit test. Where we conduct short circuit test? High voltage side. So on high voltage side, what is the rated current? You need to check once. What is the rated current on high voltage side? Volt ampere rating by voltage. 4K, 4 into 10 cube by voltage 400. How much it is? 10 amperes. Okay. This 10 amps is the full load current. So what copper loss you need in this equation? In the equation, whatever you have here, this is full load copper loss. But in the test data, they given copper loss for 6 amperes. That is wrong. Short circuit data they given wrong. So they given for 6 only. So you have to calculate first for 10 amperes what will be the copper loss. Simple one. So 6 amps, the copper loss is 21.6 watts. Now for 10 ampere, what will be the copper loss? So you know the formula, copper loss proportional to square of current. Use that. Copper loss at 10 ampere divided by copper loss at 6 ampere proportional to square of current. 10 amps means 10 square. 6 amps is 6 square. Now copper loss at 10 ampere is equal to 6 amps we have 21.6 into 10 square by 6 square. How much it is? I think 60 watts only. Is it 60? Yes, 60 watts. 60. This is the copper loss at 10 ampere or full load copper loss is this. Now substitute in equation. Therefore, efficiency at full load unity power factor we need to calculate. 1 into 4 into 10 cube into 1 divided by 4 into 10 cube, directly I am writing, plus iron loss is fixed 60, x square 1 square into full load copper loss is 60. Calculate this into 100 percentage efficiency. How much? Yes, 97.08 percentage, right? 97.08 percentage. Option B is correct. Okay, so whenever there is test data in the question, you should take care. Don't substitute blindly, that is OC test is iron loss, short circuit test is copper loss. Don't substitute blindly. You need to check the data once. They given right or wrong. If they given right, sometimes they give right only. So directly you can substitute. Okay. This is not maximum efficiency. This is not, we don't know maximum or minimum what it is. So they asked to find efficiency at full load UPF. That's why we calculated. Suppose if they ask maximum efficiency, then what we have to do? X equal to square root iron loss by full load copper loss. Okay, anyhow, X equal to 1 only you got. So maximum also same, 97.08. Maximum efficiency also same you will get, 97.08 only. Okay. Whenever in OC test they given different voltage na here, then they will give the required data for that to find, just like iron loss calculation. Okay, you will get that type of question. If you get mostly you don't get for OC, the variation they will give in short circuit only. If they given in OC, no, that is a problem of iron loss. That's it. However, you calculated in iron loss, same way you have to find here also. If they given for some other voltage, so they will give the required data at that time. Okay, Abhijit. Next question. Completed all of you. Say this one. This is previous gate question for 4 marks, common data question. First question, second question. Read the question. 300 kVA transformer has 95% efficiency at full load, 0.8 lagging, and 96% efficiency at half full load UPF. Okay, full load efficiency is there, 95%. Half full load efficiency is there, 96%. And power factor is also given at that time. Now we have to find first question, what is the iron and copper loss? Iron loss and copper loss under full load or dash. Second question, maximum efficiency at UPF is dash. Maximum efficiency at UPF. Okay, so given that efficiency under full load, power factor is 0.8 lag, that is important. 0.8 power factor is 95%. Okay, and also given efficiency at half full load, but UPF, unity power factor, two different cases given, that is 96%. So we need to find iron and copper loss. Iron and copper loss. So two equations you will get, two unknowns. You can solve just like our previous question. So first formalize, write one time formula again. Efficiency at any fraction. X volt ampere cos phi. X volt ampere cos phi plus iron loss. X square full load copper loss. Now I am applying these two equations one by one. First one. Efficiency at full load 0.8 power factor is given 95%. Same equation I will apply to this. So full load means X is 1. So 1 into, what is the volt ampere rating in the question? 300. So 300 into 10 cube. Power factor is 0.8. So 0.8 only we have to take. Divided by 300 into 10 cube into 0.8 plus iron loss plus X square, 1 only copper loss, full load copper loss. This is equal to 0.95, 95%. Now cross multiply and you will get one equation, iron loss plus copper loss. So this is you have to solve. I'm not writing completely. And don't multiply 0.95 with every value here. So what you can do, take 0.95 at this denominator and take this denominator to right side. Then simply you will get iron loss plus copper loss, one value here. Let it is equation 1. Okay. Similarly apply for second. First we applied now. Second case. Similarly, efficiency at half full load. This is at UPF given. How much it is? 96.96. Now apply here. According to same formula, X is 1 by 2. Volt ampere given 300 into 10 cube. This is at UPF 1. So 1 by 2, 300 into 10 cube into 1 plus iron loss. X square is 1 by 4 because X is 1 by 2 into full load copper loss. This is equal to 0.96. Again cross multiply. So we get one equation, iron loss plus 1 by 4 copper loss. Some value will get, solve this, you will get some value here. It is equation 2. Solving 1 and 2. Solving 1 and 2. Solve the two equations, we get iron loss and we get copper loss. Tell me that values. Iron loss is how much? Iron loss. You can substitute and you can check. You can substitute and you can check. But 4 options we have to check now there. Iron loss is 4.12 kilowatts and copper loss is 8.51 kilowatts, right? Iron loss is 4.12 kilowatts. Copper loss 8.5 kilowatts. So kilowatts I'm writing. Okay, check all of you this same. Yes. So iron loss we got. First question it is copper loss 8.5. So 4.1 to 8.5. First option on. PC means core loss. No, this is not correct. See, they given PI is the iron loss. No, iron loss PI. So what is that iron loss? 4.12. This is option C. And this is PC means copper loss. PI they indicate iron and copper. Iron loss 4.12 kilowatt, copper loss 8.5 kilowatts. Okay. First question is this. Now second question is what? What is the maximum efficiency at UPF? Now to find maximum efficiency, what we need to find? X we need to find. Where we get that? So where we get maximum is X. Calculate X now. Next, second question. For second question, X required. X equal to square root iron loss by full load copper loss. And this is we already calculated just now. 4.12 divided by 8.5. Both are in kilo. So directly, what is X value? Root 4.12 by 8.5. 0.696. This is the value of X. Now at this percentage, 69.6 percentage, you will get maximum efficiency. Therefore, maximum efficiency equal to X is this 0.696 into volt ampere, 300 into 10 cube. At which power factor they are asking? UPF. If they don't give also, you have to take UPF. See, in the question they asked maximum efficiency at UPF. Suppose they did not given that UPF. What they asked, what is the maximum efficiency? That's it. Then what you will take? UPF only you have to take. Divided by 0.696 into 300 into 10 cube plus 2 into 4.12 kilowatts. 4.12 into 10 cube into 100. What is the maximum efficiency? 96.2 percentage. Okay, all of you same? Yes, 96.2 percentage. Okay, 96.2, right. Maybe some of you may have doubt now. So why it is 2WI taken? So why I written 2WI check once? In place of that copper, iron and copper loss, directly I written 2WI. Why? At maximum efficiency, what is the total loss in transformer? Simply double the iron loss, 2WI. Both are same. You can write individually iron loss plus X square copper loss. That is also you will get same answer. Or directly simplification will reduce. In place of the total losses, I am writing 2WI. 2WI. Okay. Anything will give same answer. Condition we apply. Okay. Clear all of you this question. First we calculated iron and copper loss by using the given two conditions and then maximum efficiency. Clear all of you this one. Check once, Jitendra. Copper loss and core loss, you will get same 4.12 is the iron loss. Copper loss 8.5 kilowatts. If they ask losses at half load, yes, then directly x square we are using na anyhow in the equation x square copper loss you are using. So you can directly utilize the same equation if they ask at half full load. Copper loss only will change. Okay. Next question. So you try to solve this question. Try to solve after break. We see this question. Take a break, 15 minutes, and if you come back after 15 minutes, try to solve this. Okay. Take break. So all of you got it? Yes. The maximum kVA, at maximum efficiency, what is the load kVA? Yes, 7.9 kVA, right? And find the value of maximum efficiency at zero point 0.8 power factor. Then what is the second answer? Yes, 98.44, right? First one is 7.9 kVA, second one 98.44 percentage. And here also you need to check short circuit data only. High voltage side, na short circuit test. High voltage side, what is the rated current? High voltage side rated current 10 into 10 cube divided by voltage 2500. How much it is? 4 amperes. But what is they given? 3 amps only they given. So this is not full load copper loss. So you need to calculate what is the copper loss for 4 ampere. What is the formula? Copper loss proportional to I square, 4 square by 3 square into 45. This is 16 by 9, so 80 watts you will get. The full load copper loss is 80. Then find X value, X root of iron loss by full load copper loss. Then X value will get 0.79. Okay, 0.79. Then what is the load kVA at maximum efficiency? X into full load kVA. Full load kVA 10. So X is 0.79, you will get 7.9 kVA. Okay, similarly find maximum efficiency, but given they are asking maximum efficiency at 0.8. So you should not take UPF. Whatever they asked, you have to calculate. Okay, then you will get 98.44. Yes, right. Next question. Okay, so mostly this type of questions on efficiency. See one more. See this last question on efficiency. So last question on efficiency. A 1000 by 200 volt single phase transformer has primary and secondary resistance. R1 is given 0.25 ohm, R2 is given 0.014 ohms. Okay. Now iron loss is given 240 watts. What is the value of secondary current? We need to find what is the value of secondary current I2 at which efficiency will be maximum. At maximum efficiency, you need to find the I2. I2 is variable. I2 is changing in a current magnitude. So that I2 you need to calculate. So what is the condition for maximum efficiency? Copper loss should be equal to iron loss. So what is the formula for copper loss? At maximum efficiency, copper loss, I square R, I2 square R02. This is the copper loss. This should be equal to iron loss. Iron loss. Now why we are taking I2 square R02? Can we take I1 square R01? Yes, that is also right, but they are asking I2 na here. That's why I2 we are taking. I2 square R02. Suppose if they ask I1 in the question, then I1 square R01 you have to write. Okay, based on question. Now R02 required for us first. R02. What is meaning of R02? Total resistance referred to secondary side. Total resistance referred to secondary. So that R02 we need to calculate. There is R1, R2 individually, R02. What is R02 formula? R2 plus R1 dash. R2, what is R1 dash? Resistance transferred from primary to secondary. What is that R1 dash means? K square. Multiply that R1 with K square. Now what is K? That you can find from voltage rating. Voltage rating. So K equal to E2 by E1. Substitute here. 1000 by 200 by 1000. 1 by 5, 0.2. K value is 0.2. Now substituting here, R2 is 0.014 plus K square is 0.04 into R1 is 0.25. So what is this total? Calculate. 0.024 ohms total resistance. Now substitute in the equation condition. I2 square, we need to find how much current. I2 square into R02 is 0.024. We calculated. Iron loss they given 240. Now I2 square equal to 240 divided by 0.024. So calculate this. The final value of I2, we get 100 amperes. So this is the value of secondary current where we get maximum efficiency of transformer. See. Okay. Got it all of you, Sam? Yes, right. Suppose if they ask primary current, no. If they ask in the same question, the primary current at maximum efficiency is dash. Then what you will use? Same condition. Copper loss equal to iron loss. I1 square R01 equal to iron loss. Then R01 you have to find. R1 plus R2 dash. Okay. These are the models for calculation of efficiency. And one more, some students are asked. Now presently in online mode, so mostly total education is in online mode only, engineering colleges or institutions, anything. Now students are now in particular online mode, the students are most confusing. So previously in offline 2 years back, there is no concept of online. Means there is online, but we are not that much aware of this all, only offline. Then we are very good at that time, but now student is most confused. So they are watching different because so much content available now in the online, so much content free of cost. But my suggestion here is don't waste your time by listening that so much content there. That is not at all useful first. So whenever they are giving anything for free of cost, no, that content may not be 100% perfect, just for time pass. Now you are wasting your time by listening so many things there. But don't waste. You try to understand where it is good, what we should listen, when we should listen. So listen then only, practice then only, and leave that one. And don't again watch different lectures, and don't confuse finally. Okay. So no one will provide you complete information there with free of cost in that. So anyhow they are providing whatever it is, but I'm not saying that don't listen completely. That is your interest. So wherever you feel the perfect one or best one, you try to go through that, but not everything, because don't confuse by listening so many things. Now so many textbooks are there, for example Bimra, Nagrath and Kothari, or Fitzgerald, or any other author, JB Gupta, like this. Now are you reading all the textbooks? No. One textbook also properly we are not reading. So prefer any one standard book and go to some example questions there in standard books, like in JP Gupta or anywhere you can solve example questions, any textbook you can prefer. But for concept wise, some books like PS Bimra is best, and Nagrath and Kothari also good. And after that, you can prefer JB Gupta also. So much content will be there in that. Like that, go through that standard books after listening any classwork here. Enough. And don't see many different types of lectures, and don't confuse finally, your total subject will be gone. Okay, so maybe you people are already experienced, no need to tell all this. Now everyone is so much aware. We no need to tell anything, so everyone is so much intelligent. Okay. Yes, very good, right? Vinayak said correct. whatever it is. Yes, particularly in online teaching, so the teachers should have so much patience, so much. Sitting at one place for a long time is not easy to sit here. Actually, in physical class, we never feel this much difficulty. Uh, I1 square R01 equal to Wi, because you can, if they ask in the question to find primary current, that's why written there. You can consider if they ask primary current, I1 square R01. Any one same, I1 square R01 also same, I2 square R02, both values are same. But based on the question, we taken I2 square R02 here. Okay. Okay, anyhow, next. Up to now, we have seen power efficiency. Now we will see energy efficiency. Up to now, whatever the efficiency we have seen, that is called power efficiency. Power. Now we will see energy efficiency. Let's see what is that. Energy efficiency. This is also called all day efficiency. This is also called as all day efficiency. But I don't write it is all day because there is one reason. Observe. What is this energy efficiency? It is in energy. What is power efficiency? It is in power. So just now we have seen in the definition. What is the definition? It is the ratio of power output to the power input. So that is power we are writing. But in this energy efficiency, what we write is energy output. Output energy to the input energy. So we will write here efficiencies output energy to the input energy. So we call it is energy efficiency. Then when it will become all day efficiency? Energy efficiency is a all day efficiency. It is also called all day efficiency if you calculate this efficiency for 24 hours. So this energy efficiency you can find for one day, or you can find for 1 week also, or you can find for 1 month also, or for one year also. That is annual energy efficiency we call. Anything, that is all energy efficiency only. But all day efficiency we need to discuss, so which we have. So what is all day efficiency now? If the energy efficiency calculated for 24 hours, if the energy efficiency calculated for 24 hours, we call it is all day efficiency. Okay. If you find energy efficiency for 24 hours, it is all day. Or if you find energy efficiency for 1 week, that is energy efficiency for a week. Like that, if you find for 1 year, that is annual energy efficiency. Like that we have. But we need to discuss only about all day efficiency here. So there we write 24 hours. So same equation, whatever you have seen previously, again write the same equation, no change. How energy will get? Already we have power. Energy equal to power into time of operation. That's it. Kilowatts or watts we have power. Energy means what? Water. So the time we will multiply in duration, number of hours. How much duration load is connected. So this energy efficiency particularly we need to calculate for distribution transformers. For distribution transformers, we need to calculate energy efficiency only, not power efficiency. So based on this energy efficiency calculation, we are dividing transformer into two types called power efficiency, power transformer, and distribution transformers. And whatever we are seeing regularly, they are distribution transformers in your states. And power transformers you cannot see directly, and if you want to see, you have to go some more distance, like in transmission side, transmission lines or big substations or power plants. There we need to go to see that power transformers. Okay, first write the definition of this definition. It is the ratio of, so write this, it is the ratio of output energy to the input energy. It is the ratio of output energy to the input energy. It is the ratio of output energy to the input energy. So right below that, next line, if the energy efficiency calculated for, if the energy efficiency calculated for 24 hours, calculated for 24 hours, then it is called as, all day efficiency. Then it is called as all day efficiency. All day efficiency. Now, what is the complete equation of that? Let's write that. Therefore, below this, all day efficiency. So what you need to do is same previous equation. What is that previous equation? X into volt ampere cos phi. Right up to this same, and just multiply with the time of operation. That's it. Time. So we will see one numerical also, how to solve this all day efficiency, so that you will get clear idea on this. Divided by X into, this is output power, divided by output plus losses. Complete every term you have to multiply with time of operation. So X into volt ampere cos phi into time plus iron loss into time plus X square copper loss. X square full load copper loss it is into time of operation. For how much duration copper loss takes place, for how much duration iron loss takes place. So this is all day efficiency equation. Same equation, just multiplied with time. Power is converted to energy. That's it. What is the need of all day efficiency? So for distribution transformers, all day efficiency, if you find energy efficiency, you will get exact one. Otherwise, distribution, you will see the difference. What is the problem for power transformer and distribution transformer? You will see now. Okay, right. Side heading. Difference between power transformer, power and distribution transformer. Power and distribution transformer. Difference between power transformer and distribution transformer. So right side by side, power transformer here and distribution transformer. See, first, what is the range of voltage using for power transformer? Power transformer located in what region? Transmission region. Power transformers we have in the transmission side, and distribution transformer in the distribution side. So transmission voltage is generally very high, transmission, and distribution voltages are what? Low voltages. So this power transformer located, it is located in transmission network, and it is located at distribution network. It is located in distribution network or distribution side simply. Okay, next. The voltage range of these power transformers is generally greater than 33 kV, like 66 kV, 132 kV, 220 kV, like that. These are all power transformers. High voltage rating transformers we call power transformers. And distribution transformers range is less than that, less than or equal to 33 kV. And again in distribution, we have two types: primary distribution, secondary distribution. And from which transformer you are getting supply? Secondary distribution transformer. So whatever the supply we are getting, that is secondary. Now what is primary means? See, first from the transmission, the power or supply will come to first substation, not directly to your home. No, is that supply directly coming from transmission to your home? No, first it will go to a common substation. So in the substation, the range is 33 kV will come to substation. There, that 33 is stepped down to 11 kV first. 33 kV is stepped down to 11 kV. This is our primary distribution. The primary distribution is 33 by 11. Now secondary distribution is 11 kV by that 440 volts. Now this is our secondary distribution transformer. From here only we are getting supply finally to the loads. Okay, from here you are getting supply 11 kV by 440, three-phase transformers. Okay, so all that less than 33 kV we call distribution transformers. Next important difference, observe. Out of these two transformers, power transformer and distribution transformer, in which transformer load is 24 hours connected? Suppose if you take transformer in your street, on the transformer same load is there in 24 hours? No. Daytime generally less load, then evening time little load increase, and night time still load increase. Again in the early morning again load decrease. So fluctuations will be there, no? So like that, if you take a distribution transformer, load fluctuation is more. But if you take power transformer, this is located in the transmission side. So it is supplying power to so many transformers. So with this, if any small transformer also load variation is there, there is no big variation on the power transformer, because distribution transformer supplying nearby, suppose 10 houses, distribution transformer. In every house, same load will not be there. Different load fluctuation is more. But power transformer is supplying some hundreds of transformer. So what is the load fluctuation on that? Because when you take more number of transformers, the load fluctuation on the main transformer will reduce, or continuously it will supply some power to one transformer or some other like that. See, if one is underloaded, one will be overloaded, or one is having load. So like that it will be balanced. So power transformer fluctuations is less compared to distribution transformers. Okay. So write that point first. It is loaded 24 hours. It is loaded 24 hours. So almost 24 hours load will be there on this power transformer. Next, distribution. It is loaded based on load cycle. It is loaded based on load cycle, but not same 24 hours. Load cycle means what? Every duration. Suppose in 24 hours, from 4 hours, for 4 hours there is some load, and for remaining next 2 hours there is some other load with load variation. They will give one load cycle. So you will see that in the question. I will show you that what is load cycle. Okay, so load fluctuations are less in power transformer, and load fluctuations are more in distribution transformers. So write that point. Load fluctuations are less. Next, in distribution, load fluctuations are more. Load fluctuations are more. Next point. Next point. Next, in power transformer. Now tell me, there is a load mostly 24 hours. There is a load mostly 24 hours on power transformer. Then iron loss and copper loss 24 hours will take place or not? Yes, 24 hours losses will take place. But observe distribution transformer. When there is load, there is a copper loss. When there is no load, is there copper loss in transformer? No copper loss. So in distribution transformer, iron loss will take place 24 hours, but copper loss will take place based on the load connected. Okay, but in power transformer 24 hours we have load, so iron loss is there continuously and copper loss also there 24 hours, both will be there. But in distribution transformer, iron loss 24 hours. Why 24 hours? Why 24 hours? To the transformer, supply voltage is there or not? Yes, supply voltage is there. 24 hours it is there, but secondary side load is not there. So due to that, iron loss 24 hours, but copper loss is only depends on load. Okay, so write that point. Write this. Both iron and copper loss takes place 24 hours. Takes place 24 hours. Next, distribution. In distribution transformer, only iron loss takes place 24 hours. Right here. Only iron loss. Wi means iron loss takes place 24 hours, but copper loss depends on load cycle. Copper loss depends on load cycle. So it won't take place 24 hours. Okay. Next point. Now tell me, as both iron and copper loss takes place 24 hours in power transformer, which loss we need to take care? Generally, which loss is greater at higher loads? Copper loss. Iron loss is fixed one, but copper loss is increased when load is high. So mostly power transformers will operate nearly full load only. Full load means copper loss is always greater than iron loss. So which loss you should take care of? That is, we should make minimum as much as possible copper loss. So we should place the copper loss, or we should consider the copper loss is as much as possible minimum in power transformer. We should write this point. Copper loss should kept minimum. Copper loss should kept minimum since it is taking place 24 hours. It is taking place 24 hours because this magnitude is greater than iron loss. Copper loss is greater, nearly full load condition. Next, in distribution transformer, which loss we should take care? Iron or copper? In distribution transformer, which loss we should kept minimum? Iron loss or copper loss? Yes, iron loss. Why? Iron loss is taking place 24 hours here, but not copper loss. Copper loss not is taking place 24 hours. Whenever there is a load, there is a copper loss. That's it. So we should take care of iron loss in distribution transformer. Write that point. The iron loss Wi should kept minimum since it is taking place 24 hours. It is taking place 24 hours. Now here the important task is how to kept minimum that iron loss. So important question in interviews also, many times this question people is faced. See, the question, listen carefully. So there is a transformer of rating some 33 by 11 kV. Okay, there is voltage rating, power transformer is there, same voltage rating, there is a power transformer, there is a distribution transformer. There is a power transformer. One transformer is called power transformer. One transformer is distribution. In front of you, both are there, and both same ratings, 33 by 11 only, and both having same kVA also, 100 kVA only. But one is power transformer, one is distribution transformer. Now tell me, which size is bigger? Which one is large in size? Power transformer or distribution transformer? The size of which transformer is large? Power transformer or distribution transformer? Okay, same I expected. So most of you given power transformer. Okay, enough. So most of you given power transformer, size is big one, but the answer is distribution transformer. For the same voltage rating and power rating, power transformer is designed, distribution transformer is designed. Then which transformer size is large? Distribution transformer size is large. You can easily identify this. Bigger one is distribution, small one is little small one is power transformer. The reason is from this point only. So we need to keep iron loss minimum in case of distribution transformer. How can we keep minimum it is? How can we kept minimum? Tell me. To kept iron loss minimum or to reduce iron loss in a transformer. What is iron loss? Sum of two losses. Hysteresis loss, eddy current loss. Okay. Hysteresis loss and eddy current loss. Now we know very well the two equations. Hysteresis loss proportional to Bm power 1.6. Eddy current loss proportional to Bm square. Okay. So are you remembered now these equations? So total equation I'm not writing, only that flux density I'm writing here. Bm power 1.6, Bm power 2 square. Okay. And what is the flux density relation? Flux per area. Okay. Flux density means flux per area. Now, if you want iron loss to be reduced, you have to reduce hysteresis loss and also eddy current loss. How to reduce? And from these relations, to reduce hysteresis loss and eddy current loss, mainly you need to reduce the density, flux density of core. Flux density of core. What is the flux density formula? Flux per area. To reduce flux density of any core, what we have to do? Increase the area of cross section. Increase area of cross section of core. So whenever area increase, density decrease, then losses also decrease. So overall iron loss also decreases. So area of cross section increases means size of core increases. Then your size of transformer tank also increases. Now which one is larger in size? Distribution transformer. Clear? So in order to keep that iron loss minimum, why minimum we have to reduce? Because iron loss taking place 24 hours here. So that if you reduce that, your efficiency little increases. For that reason, we need to keep minimum, that is. For that, what we have to do? We need to design the cross-section area for bigger one. Okay. So remember these points. And finally, what is the efficiency used to find the performance of power transformer and distribution transformer? Right, that last point. Last point. So for power transformer, the efficiency used is called power efficiency. Therefore, power efficiency is used for power transformer. For power transformer, power efficiency, output power by input power. But for all day distribution transformer, we use energy efficiency or all day efficiency. All day in bracket, right? Energy efficiency, that is. Energy efficiency is suitable to find efficiency of distribution transformer. To find efficiency of distribution transformer. Why energy efficiency? Because in distribution, load is changing time to time. then you cannot write power efficiency here. Now I will show you why power efficiency is enough for power transformer. Observe now. Observe. Taken this point. Completed. Observe here. See, if you write power transformer for distribution transformer, and for this one, for example, what is the efficiency formula? X into volt ampere cos phi. If you write energy efficiency for power transformer, it won't satisfy. You will get power only again. Check what happened. For power transformer, I am writing efficiency. If you write energy also for this, see, x volt ampere cos phi into time. How many hours there is a load on power transformer? 24 hours. So write 24 time divided by x into volt ampere cos phi into 24 output plus iron loss. How many hours taking place? 24 hours. 24. And how many hours copper loss is taking place in power transformer? 24 hours taking place. Then 24 gets cancelled, both numerator denominator. Then again it is coming in the form of output power by output power plus losses. So even if you use energy efficiency for power transformer, you are getting finally power efficiency only. So power efficiency is suitable. Power efficiency is suitable for power transformers. But for distribution transformers, this output will not be present for 24 hours. For some duration, there is no load on transformer also possible. Then time will not satisfy. Output iron loss only 24 hours. So now write the exact all day energy efficiency equation. Now clear why energy efficiency not suitable for power transformer? Because of this reason, 24 gets cancelled. If you write energy efficiency also for power transformer, it will come again power efficiency only. In terms of power only you will get, output power only you are getting. Here you written energy, but finally you got again power only. Okay, right. Right here, make a note. Note the all day efficiency. The all day efficiency of distribution transformer is given by distribution transformer is given by, so remember this, all day equal to x volt ampere cos phi into time divided by x volt ampere cos phi into time plus, in place of iron loss you write directly 24 hours. Time is in hours. This t time is in hours. Is in hours. Okay, if you see one numerical, you will understand how to find these all day efficiency. And x square copper loss, this is multiplied with time again. Okay, only iron loss in this equation you should multiply with 24. 24 hours it will take place, but remaining power output power and copper losses depends on duration of time. See, I will give you one question on this. So same model, you will get efficiency, all day efficiency problems. See the question. How to reduce copper loss in power transformer? Previously we have seen here, copper loss should kept minimum. So for that, you need to use a superior quality of copper material. Superior copper wire, good quality of copper wire we should use, so that resistance is as much as possible less for that, I square R loss also reduce. Okay, for power transformer. Now, write the question. Question on all day efficiency. Write this. A 5 kVA single phase transformer. A 5 kVA single phase transformer has a core loss of 40 watts and full load ohmic loss of 100 watts. Full load ohmic loss of 100 watts. So don't leave. So maybe some of you at the last generally will leave, but don't leave. So we start voltage regulation. If you do, if you don't have the idea of that starting definition of that voltage regulation introduction part, tomorrow you cannot understand anything about voltage regulation. Okay, so stay. We will see voltage regulation also now itself. The daily variations. The daily variation of load on transformer. The daily variation of load on transformer is given that, see, 7 a.m. to 1 p.m. given the load is 3 kilowatt at 0.6 power factor. Next, 1 p.m. to 6 p.m. given the load on transformer is 2 kilowatt at 0.8 power factor it is. Similarly, 6 p.m. to 1 p.m. the load on transformer is 6 kilowatt load. This is at 0.9 power factor, and 1 this is 1 a.m. 1 a.m. Next, 1 a.m. to 7 a.m. no load on transformer. No load. Okay, so we have to find the all day efficiency of transformer. Find all day efficiency. Find all day efficiency of transformer. Find all day efficiency. See, the iron loss of transformer will never change. What is the iron loss given? Core loss of 40 watts. So given in the question, the iron loss is 40 watts. It never changes. It is fixed. 24 hours it will take place. Next, observe 7 a.m. to 1 p.m. 7 a.m. to 1 p.m. What is the duration? 6 hours. Okay, this is 6 hours. Next, 1 to 6 p.m. What is the duration? 5 hours. This is for 5 hours. And 6 p.m. to 1 a.m. again. 6 p.m. to 1 a.m. 6 plus 6 and 1. 7 hours. 7 hours. And 1 a.m. to 7 a.m. again it is 6 hours. Okay. So total 24 hours. In a day, for some duration there is some load and some other duration. So like that load is given different. Now whenever load is changing, which loss will change? Copper loss only will change. So that copper loss you need to calculate in each and every duration. In each and every duration, you need to find copper loss. That is the first step we need to do in all day efficiency problems. Okay, how to find that copper loss in every duration? See, they given full load ohmic loss of 100. Full load means what? This 5 kVA This 5 kVA is the full load kVA. 5 kVA is full load. Now convert this given load into kVA. How to convert into kVA? We have the equation from power factor or power triangle. This is power triangle. P, Q, S, apparent power, and this is the power factor angle. From this, what is cos phi? Cos phi is what? Adjacent side by hypotenuse, means P by S, kW by kVA. Then if you want kVA, kVA means S, that is equal to kW, P means kilowatts, divided by cos phi. So there is kW power factor, kW power factor, kW power factor. So convert all into kVA, volt ampere rating. Convert all into volt ampere rating. This is how much in kVA. This is 3 kilowatts divided by 0.6, 3 by 0.6. First one, 5 kVA. Okay. Next, this one, second load is 2 kilowatt. So 2 by 0.8. Calculate how much? 2 by 0.8. This is 2.5 kVA. Next, this is also the kVA rating of this load is 6 by 0.9. Calculate how much? 6 by 0.9. Yes, 6.67 kVA. Okay, 6.67. And for fourth one, 0. This is 0 only, no? No load. No load means copper loss 0. So for 5 kVA, see, for 5 kVA, 5 kVA means full load, because they given rating 5 kVA in the question. So that is full load kVA. So for 5 kVA given copper loss is how much? 100 watts. For 5 kVA, copper loss is 100. Okay. Now first load duration. What is the kVA we got? First. This is first, second, third. Now for first, how much we got? 5. 5 kVA means copper loss remains same or not? Yes, copper loss is same only. So for 5 kVA, copper loss same, 100 only. Already they given for 5 kVA 100, so this is 100 only. Next, second load duration. Second, what is the second kVA we got? 2.5. 2.5 means exactly half. If full load copper loss is 100, what is the half full load copper loss? 1 by 2 whole square into full load copper loss, half. So we have the formula, copper loss at any fraction x equal to x square into full load copper loss. Previously we have seen in the losses. Then exactly 1 by 4 times of that. So I will write anyhow, copper loss in second equal to 1 by 4 times of full load copper loss, 100. This is 25 watts. Clear why I written 1 by 4? So we have formula, copper loss at x, any fraction full load equal to x square times of full load copper loss. This is I applied. Okay. Next, third one, copper loss in third case. What is the kVA rating in third one? 6.67. More than 5, more than full load it is. More than full load. Then definitely more than 100 watts. Then how to find that? Yes, you can find that. Copper loss in third is 6.67 kVA. Actual full load is 5 whole square into 100. See, copper loss proportional to square of current. In place of that square of current, I am using that kVA square directly. kVA square directly I am applying, because current is not there. kVA only we have. So that kVA directly I used, because kVA proportional to current only now. kVA is what? Voltage current. Anyhow, voltage is constant. kVA proportional to current only. So that is I taken kVA square. So copper loss at 6.67 divided by copper loss at 5 kVA. What is the relation? 6.67 square divided by 5 square. Same I applied here. Now how much it is? Calculate. 177.9 watts. Okay, got it all of you same? Yes, good. 177. Now we got the copper loss in every duration. Now over. Easily you can find. Therefore, write all the efficiency equation. Problem is over. Only thing in this all the efficiency is calculation of copper loss. That's it. Then you can directly substitute. Therefore, all day efficiency. What is the formula? X volt ampere cos phi into time. So we have total three durations, three different durations. So at each case you have to write directly. This is output power. Directly they given power 3 kilowatt, and no need of that X volt ampere cos phi individually, because you no need to write. Directly they given 3 kilowatt. No, X volt ampere cos phi means VI cos phi power only. No, that is active power. They directly given 3 kilowatt. So you can directly substitute. Otherwise, if you have doubt, X means full load 1. So these are all again calculation increase. So directly 3 kilowatt, 2 kilowatt, 6 kilowatt, directly you can substitute. See, 3 kilowatt, 3 into 10 cube, power into time. How much duration it is? 6 hours. 6 hours. Okay, first one I written, plus second duration of load 2 kilowatt. How many hours it is? 5 hours. So 2k into 5 hours. 2 into 10 cube into 5 hours, plus, so I'm writing total output in different durations. Third one is what? 6 kilowatt. How many hours it is? 7 hours. 6 into 10 cube, 6 kilowatt into 7 hours. Okay, total output I written, divided by, again write the same output here. Total all three you have to write. 3 into 10 cube into 6, plus 2 into 10 cube into 5, plus 6 into 10 cube into 7. This is output. Same output again I written, plus iron loss 24 hours. What is iron loss given in the question? Iron loss is 40 watts. 24 hours it is. 40 into 24. Okay. Iron loss is over. So follow step by step. Output by output plus iron loss. 24 hours we have to take, because it will take place 24 hours. Next, plus copper loss. Three durations we have now. Individually we calculated copper loss here. First one is 100, second one 25, third one 177.9. First one is 100 watts. How many hours first load cycle? See, first one is 6 hours. 100 into 6 hours, plus second duration. Second is 25 hours. How many hours it is? 5 hours, plus third one is 177.9. 177.9. How many hours it is? 7 hours, a third duration. And for remaining duration, no load, no? That's why copper loss also 0. So three different outputs in three durations. For accordingly, copper loss we calculated and substituted. That's it. This is all day efficiency. Find this value, how much? Find this. Output by output plus losses. Same equation we written, just multiplied with time of operation. Tell me what is the answer? Efficiency. Yes, good. 95.98%. Right. See, X you no need to take again now. So already a given statement. Why X is not required here? Because directly they given active power in the data. So X is not required. X volt ampere cos phi is active power. That active power directly they given 3 kilowatt. So substitute directly. Yes, answer is 95.98%, or approximately 96%. Okay, this is the calculation of all day efficiency. 177.7 Okay, whatever. So 177 approximately take, or 178 take. Okay. Voltage rating not required in the question. Voltage rating not required for efficiency calculations. Voltage rating not required. KVA rating is enough. With that you can solve. Third case is overload condition. Yes, that is overload. Sometimes it may overload also, no, in some duration. But overload, people will say that it will damage, not immediately. Suppose if overload duration is continuously present 24 hours, then heat is very high, then it may damage. So overload for some time, no problem, no problem. Okay. So with this efficiency, we complete. See, what is the important thing in all day efficiency? Calculation of copper loss. Calculate copper loss in the given load cycle individually. So for that we calculated kVA first. Why kVA we calculated? Because in the question they given 5 kVA. That indicates that that is the full load kVA of transformer. Now for that full load they given ohmic loss. Ohmic loss means copper loss 100 watts. Now according to given load we got different kVA ratings. So accordingly copper loss we calculated, and that is substituted in equation. That's it. Ankur, why losses I'm not taking 5 kVA because copper loss proportional to square of current. But do you have current here? No. But what we have in place of that, with respect to kVA, directly we are calculating. 5 kVA copper loss is 100. Now for 2.5 kVA, what is copper loss? 2.5 means half load. Then half load means directly 1 by 4. Like that, copper loss proportional square of current. In place of that, kVA square directly we use. kVA square directly you can use that because kVA proportional to current only, no, voltage is constant in that, so you can use that, you will get copper loss. So based on the question we need to proceed. Okay, next, the second performance parameter is what? Voltage regulation of transformer. This voltage regulation topic you will get again in alternators, that is synchronous generators, and again you will get in DC generators. So this voltage regulation we calculate for voltage generating devices. So where we voltage generated, transformer voltage generated, EMF induced, generators EMF induced. So wherever EMF induced, there we will find voltage regulation to know the performance of that device. That may be transformer, that may be generators, that may be DC generator or synchronous generator. So if you understand voltage regulation of transformer well, now already if you understand this now you no need to go through synchronous generator or voltage regulation, DC generator voltage regulation. Conceptually you got almost same everywhere. Voltage regulation is same whether it is generators, whether it is transformer. So if you understand well here, already you got, that means that already you got synchronous generator voltage regulation also, and DC generator voltage regulation also you got. Conceptually you got, but mathematically some equations will change in generator and transformer. Okay, so try to understand clearly here. It will be very easy to you in the next topics like synchronous generator or DC generators. Okay, right, starting voltage regulation. Second, voltage regulation. What is regulation? Simply change in any value. Change in any value we call regulation. So voltage regulation, change in voltages. Similarly, speed regulation we have in motors. What is speed regulation? Change in speed. Changes in speed when load changes. Like that in generators or transformer also, whenever load is changing, regulation will change. So now that we have to calculate voltage regulation. Now, to for the statement or definition of this voltage regulation, we need to consider equivalent circuit of transformer first. Okay, same I'm writing. Right. Consider the equivalent circuit of transformer refer to secondary Now I am drawing circuit refer to secondary side completely. Secondary side. Why secondary side? Because where we connect load, secondary only, no load is connected. That's why secondary I'm taking. So this is the circuit. R02, X02 and load. So I drawn equivalent circuit refer to secondary side. So complete resistance I will transfer to secondary, reactance also transfer to secondary. And no load we are not considering, neglecting that no load branch because small no load current. R02, X02 switch, and this is our load. And what is EMF induced secondary side? E2. EMF induced is E2. And voltage across the load we are getting is V2, terminal voltage. The terminal voltage is V2 always. Voltage across load, that may be generators or that may be transformer, V2 only. Terminal voltage we call. Okay. Now switch is under open condition, so no current first. Now once you close the switch, now load is connected. That means that a current I2 will flow. A current I2 will flow through this winding. Now whenever there is a current, some drop will takes place in resistor. Then the voltage drop due to resistance is I2 R02. And whenever current flowing in reactance, there is a drop here I2 X02. Then some voltage will appear here. That voltage is V2, terminal voltage. Okay. Now, what is voltage regulation? Simply is the change in voltage across the load from no load to full load. The change in voltage. So listen carefully. In definition only, I will tell the important statement regarding generators and transformer because there is a slight difference. You people will know only when generators is completed. Transformer we take little change. Generators we take some other. So what is that difference? I will tell you now. Listen carefully. The voltage regulation is the change in voltage across the load from no load to full load condition. No load to full load. But every textbook will make a small mistake here. No load to full load you should not say. No load to any load. No load to any load. But generally the standard books also will take no load to full load directly. Because what is the maximum capacity of transformers or generators? Full load. That's why they will take full load and they will calculate voltage regulation. But I will say that you should not say the voltage regulation definition as no load to full load always. It is not no load to full load. No load to any load, because a transformer may supply full load or less than that, that is half full load or 70% or 80%, anything it can supply, no? Okay. But according to standard books only we follow here. But I will give this point as a note. You should remember this point. Okay. First write the definition, then we come back to this figure. I will show you what it is. Right. Definition. It is the ratio of it is the ratio of change in voltage across the load across the load from no load to full load, from no load to full load to the no load voltage, to the no load voltage at a specific power factor of load, at a specific power factor of load, at a specific power factor of load. It is the ratio of change in voltage across the load from no load to full load to the no load voltage at a specific power factor of load. So if you write in equation, the voltage regulation is ratio of change in voltage from no load to full load. No load voltage is E2, full load voltage means V2 change. So I will show you that in the figure what it is. Divided by no load voltage. No load voltage is E2. So this is called voltage regulation. Now come back to figure. Observe this. Now I will show you with a small numerical example so that you will understand clearly. See, let us considering E2 is some 200 volts, for example. E2 is 200. Now I will place 1 voltmeter across the load here. Suppose a voltmeter I placed between these 2 points. Initially switch is open. Switch open. Switch open means no load condition it is. Load is not connected. Now tell me what is the volt. Is there any current here first? If switch is open, is any current will flow? No current, because current required closed path. So no current. Now tell me what is the voltmeter reading? How much voltmeter will show now? Under no load, what is the voltmeter reading? 200 only, no? 200 only it will show, because no drops, directly the same voltage will appear in this meter. So the no load voltage is E2, same voltage, that is the no load voltage is 200 volts. The voltmeter showing 200. Okay, clear up to this? Now let us close the switch. Switch is closed. Connected. Load is connected. Assume that the load is full load. Assume the load connected is full load. Full load means what? What is full load? That depends on transformer capacity. Suppose this transformer capacity 10 kVA. So I connected a load of 10 kVA only. So that is called full load. So load is connected, which is full load. Now under that full load, same voltmeter I placed. Now how much, as load is connected, a current I2 is flowing in the circuit. So some drop in resistor, some drop in reactance. Then how much voltmeter will read? Tell me. Less than 200 only, no? 200 you don't get now. Some voltage drops. Some voltage drops. So you will get let approximately 190 volts. So how much change observed across the load from no load condition to full load condition? 10 volts is change. And this voltage change is expressed as again no load voltage. So change, no load voltage means E2. Full load voltage means this V2. So that E2 minus V2 is the change in voltage across the load. E2 minus V2, 10 volts divided by no load voltage, E2. That is called the per unit voltage regulation of transformer. Both voltage by voltage only, no? So that is per unit voltage regulation. So that is I written here. And if you want percentage voltage regulation, simply multiply with 100. E2 minus V2 by E2 into 100. This is percentage regulation. Okay, percentage regulation. Now listen. For generators, same definition. Alternator or DC generator also same definition, but in place of this no load, at the denominator, like this we write the equation. For generators, E minus V, change in voltage, E minus V divided by V. This is we write in generators. That may be DC generator or synchronous generator. E minus V by V we write. It is expressed, the change is expressed as terminal voltage in generators. Okay, this difference you will see in transformers and generators. Both the DC generator, synchronous generator, this is the equation. But only in transformer, we write in the denominator no load voltage. What is the reason for this? Why we are writing like this? Because if you see the transformers nameplate, we have some voltage ratings, for example 400 volt by 200 volt. What is that voltage rating on transformers? E1 by E2. Okay, similarly for alternators or DC generators, we write a three phase 400 volt 50 hertz alternator. What is that 400 volt uh, given in that nameplate of alternator? On the nameplate also you will see that 400 volts. What is that 400? That 400 volts in alternators is terminal voltages always. The voltage rating indicated on generators is always terminal voltage. But in transformers, the voltage rating given is always no load voltages. E2 they will give. E2 means what? No load voltage. But full load voltage they don't give. That's why we will consider the denominator no load voltage in transformers, and in generators terminal voltage. Okay, and one more reason is, according to our Indian standards, for transformers we always express the regulation in no load voltage only, but for generators we express it as terminal voltages. Okay, which voltage is greater? No load voltage is greater or full load voltage is greater? People will confuse here. Full load means high voltage they will feel. Which is greater? Observe here. This is no load, this is full load. Which voltage greater? No load voltage is greater always. No load voltage is greater. So in transformer, at the denominator we have no load voltage, which is higher value, no, when compared to full load voltage. Yes, that's why the voltage regulation of transformers is generally less when compared to generators. But in the generators, denominator is what? Full load voltage. Full load is less voltage when compared to no load voltage. So this is less voltage compared to no load voltage. That's why the regulation little higher value you will get in generators. So these are all interview questions. What is the regulation of transformers and generators? Which is greater generally? Practically, which is greater? Generators regulation is greater. Transformer regulation is less. What is the range of transformer regulation approximately? 4 to 10%. The transformers voltage regulation practically is 4 to 10%. And what is the generators regulation practically? That is 10 to 20%. 10 to 20% for generators. Higher values for that. So why it is higher? What is the need of higher voltage regulation? Which is important? Which is a good one? High regulation is good or low regulation is good? Low is good. Low regulation is good, but not high regulation. High regulation means, regulation is what? Simply observe here. No load to full load. How much voltage drops? No load to full load, 10 volts drop. Or if no full load voltage is suppose 180, then what is the change from no load to full load? 20. Means more voltage drop in transformer. So if drop increases, regulation increases. So which is best? Less voltage drop is best. If most of the voltage drops in the winding itself, what voltage will go to load then? So what is our main aim? To supply to loads or to supply to the winding itself? To supply to the loads. For that we need less voltage drop in the windings, so that most of the voltage will go to load only. Okay, so regulation should be less. Transformer regulation is generally less compared to generators voltage regulation. Clear all of you this definition? Now here I given at a specific power factor of load. This regulation mainly depends on load power factor. We have different types of loads: lagging, leading, UPF. So whenever load power factor changing, regulation also change. So make a note. Note. So it is note first point, voltage regulation of generators it is. No load to full load to the full load. Make a note. Note. Second point. In practical, the voltage regulation can be calculated. The voltage regulation can be calculated at any fraction of full load. At any fraction of full load. Full load, but not only at full load. But not only at full load, because in the definition I given no load to full load only, but actually it is defined for everywhere, not only no load to full load, no load to any load divided by no load voltage is called voltage regulation. This is the correct statement, but according to standard books previously we written that no load to full load. Okay, next, third point. The voltage regulation mainly depends on type of load power factor. That is lagging power factor, UPF, and leading power factor. Voltage regulation will change. Depends on lagging power factor, UPF, leading power factor. How it will change clearly we will see in the phasor diagrams. And fourth point, the regulation is positive, comma, 0 and negative based on load power factor. So direct questions on this regulation is, the regulation of transformer is 0 at which power factor? Lagging, leading, UPF. Many times alternator also same question in previous gate it is we have. The alternator regulation is 0 at which power factor? Regulation may be positive, it may be 0, it may be negative. That depends on load power factors. If it is lagging, you will get positive regulation. If it is UPF, also positive regulation. But if it is leading, you will get three types of regulations: 0, positive, negative. All three types of regulations you will get in leading power factor. So I will show you all this, how it is we are getting. If you understand here, you can forget about alternator. Alternator also completed. Same it is, almost same, 90% same. Okay, let's see for first one, lagging power factor case. And before that, go to the previous, this one. Observe this figure. Observe this. Apply KVL in this figure. Apply KVL. Then this is the EMF induced, like a source voltage it is. And this is the voltage across the load. Now, how we write KVL equation? If you apply KVL, the equation we will get is E2 equal to vector addition, because AC now it is E2 equal to terminal voltage V2 plus drops here, I2R02 drop plus JI2X02 drop. I2X02 drop. See, EMF induced is the sum of output voltage plus drops. This E2 equal to total sum of this voltage and this voltage, that is KVL we written. So using this equation, now we will draw phasor diagram for different power factors. There only you will understand how it is positive, negative, 0. What is the meaning of positive regulation, negative regulation, 0 regulation? We will see here. Okay. So take this equation. This equation we use for phasor diagram to draw the phasor diagram for different loads. Only one case we will see today. Okay. Case one, lagging power factor only we see today. Write that case one. So don't leave. This is only important. Case one. Case two, case three, you can also draw directly. Once you listen case one. Right. Case one. Case one. If the load on transformer is lagging power factor. Write that. If load on transformer is lagging power factor. Lagging power factor means what type of load? RL load. So practical cases, this is only RL load only, na, mostly. Practically the loads on transformer is lagging power factor only. Now for this we need to draw this equation as phasor diagram. E2 equal to V2 plus I2 R02 plus J I2 X02. Okay. So listen carefully this phasor diagram. In all these phasor diagram, we will consider the reference is terminal voltage. So not only for transformer, for alternators also we consider terminal voltage as always reference. Okay. So same thing I am considering. So little big diagram, draw it is. Start in a fresh page. Let this is my reference V2 terminal voltage. First draw V2 terminal voltage as a reference. Anywhere you can draw this line. Anywhere here, like straight up, you can draw like this or draw like this. So whatever the direction you want, draw it. This is V2. Now what is the load we taken? Lagging. So lagging means let sum cos phi equal to 0.8 lag. Power factor is 0.8 lagging example. Whenever it is lagging, the current I2 lags this voltage by angle phi. This is I2 lags voltage by some power factor angle phi. Okay, lagging. That's why current lags. So this is vector direction, no, anti-clockwise. Vectors will rotate anti-clockwise, and some people ask why anti-clockwise. So this is the conventional direction we follow for vectors. Always anti-clockwise direction. Okay, anywhere, not only in machine cities. So I2 lags. Clear up to this. Now once there is a current in the winding, there are two drops, I2 R02 drop, I2 X02 drop. Then if you add the two drops to the voltage, you will get EMF. Okay. Now where is the resistance drop? How to draw resistance drop? Resistance drop parallel to current always or in phase with current. This is I2 R02. So you should know all these points. In networks you will get all these. Resistance drop in phase with current. Resistance drop in phase with current always parallel to current. That's why I drawn parallel to current. Next, where is the reactance drop? This I2X02 perpendicular to resistance drop. So from here, draw perpendicular I2X02. So this is I2X02 perpendicular to resistance drop. I2X02 drop perpendicular to resistance drop. So V2 is there, I2R02, I2X02. Now what is the sum of all these three vectors? E2. Therefore, the resultant is E2. Now simple, what we did here, just this equation we have drawn as a phasor diagram. For what load? Lagging power factor load. Same as it is we have to draw for remaining cases also. Now we need to calculate regulation. What is the regulation means? What is regulation? E2 minus V2 divided by E2. This is only, no? So anyhow, denominator always positive value. E2 some positive value. Now we need to check this difference. So regulation is proportional to difference of these two voltages. Based on this only you get a positive value, negative value, zero value. So when positive, if E2 greater than V2, positive, the difference is positive. When zero regulation, if E2 equal to V2, zero regulation. When negative, If E2 is less than V2, you get negative value here, means negative regulation that is. Okay. Now observe the figure. Positive regulation or what regulation you are getting? Check from the diagram. From the figure, check it is. This is the magnitude of V2. From this is 0, let O reference. From this point O, this is the magnitude of V2 and this is the magnitude of E2. Tell which magnitude is greater from the diagram. E2 greater, no. Therefore, as E2 greater than V2, we get the value is positive. Since E2 is greater than V2 from the figure. So the regulation for lagging power factor is always positive only you will get. Regulation positive indicates what? Some voltage drop. Voltage drop is there, some voltage drop, maybe 10 volts, 20 volts, whatever it is. So that regulation of transformer is positive for lagging power factor load. Now how much magnitude, how much it is, that is we need to calculate. Okay, so quickly I will give this how much magnitude, so you have to write quickly at the same time. See, we need difference. E2 minus V2 we need to calculate now, then only we get how much regulation that is. See, same diagram, little I am extending now, check carefully. This is V2, I'm extending this line. Okay, next this is E2. If you draw a circle or arc of radius E2, how much you will get from this? As a radius or semicircle, suppose I am drawing. Okay, like this. This is E2. So I drawn a arc here of radius E2. Then this arc is intersecting this line, that is V2 line at this point. That means that if it is point O, see, if it is point O, so I'm taking, this is point A, and this is, I will draw one perpendicular. This is point B, and I will take perpendicular from here also. This is point C, and this is point D. Okay. Now E2 minus V2 means, tell, we need E2 minus V2, this magnitude required for us. E2 means OD or not? E2 means OD or not? Yes, same magnitude. I extended on this line, OD. V2 means OA or not? Yes, V2 magnitude is OA. Okay. Now OD minus OA we need to calculate. But what is OD minus OA? This is AD. Okay. Follow carefully. OD minus OA, AD. What is AD now? AB plus BC, AB plus BC plus CD. Okay. All this we have to add. Then we get how much magnitude. But in this figure, there is a problem. This CD we cannot calculate. CD is very, very small actually. Very small, that is. If you draw exact arc and if you take perpendicular from E2, this CD you will get very small magnitude, that is CD is very difficult, because when there is a right angle triangle, you can find the magnitude of these sides easily by applying the right angle triangle angle. But what is this? From here to here, this dotted line is a arc, no? This is a arc. This is not a straight line. This is arc. So arc means we cannot find. So it is very difficult to calculate this distance. We cannot find this. That's why CD we cannot calculate totally. So what we are doing is approximately, by neglecting that CD, we calculate only AB plus BC, neglecting that small magnitude CD. CD we cannot find. That's why we are neglecting in the diagram. Now we have to find AB plus BC. That's it. Once you find AB plus BC, you will get the voltage regulation. Okay, right. Therefore, so complete this diagram quickly. AB plus BC we need to calculate. Now What is this angle? Tell first. This angle how much? Whatever angle is there, phi, same angle na it is. Phi only it is. Same angle because I2 R02 parallel, and this line is straight line, same for both. So phi only it is. Now what is this angle? This angle is how much? Observe carefully. Phi is the angle between this line I2 R02 and this dotted line. Okay. Now check to this dotted line. To this dotted line, this dotted line is perpendicular. These two are perpendicular. And to this I2 R02, this line is perpendicular. Then whatever the angle is coming here phi, same angle you will get here phi. So you take the figure little big one so that all angles and magnitudes you will understand. So that angle also phi. Angle is phi. Now easily we can find AB and BC, and see this is extending little this line, and I'm same straight line perpendicular I'm extending up to this. So I will consider this is A, B, C, D, and this line is E, and this point is F. BC equal to EF. So BC equal to EF. This is C. BC magnitude is nothing but EF magnitude, because with respect to this is let this point is G. Okay, first complete. In next page I will write clearly all this. Next, therefore E2 minus V2 equal to approximately it is AB plus BC. AB plus BC. AB required, BC required. Now from right angle triangle, ABF. ABF. Observe ABF, right angle triangle. ABF. What we require to find? BC we require to find. AB we require to find. AB. How to find AB? Phi angle we have here. Apply cos phi to this. Cos phi. What is cos phi? Adjacent side by hypotenuse. So cos phi equal to, adjacent side is AB, hypotenuse is I2 R02. Then what is the magnitude of I2? AB, magnitude of AB is I2 R02 cos phi. Okay, AB we got. AB we got. Now BC we need to calculate. So same as it is applied for the previous diagram. For which triangle now? See, FEG. FEG, to this right angle triangle, apply FEG here, right angle triangle FEG. Apply here angle we have phi, then apply sin phi here. Why sin phi? Actually we required BC, but BC directly we cannot find from this diagram. But which one we can find? EF you can find. EF. EF magnitude, BC magnitude, both are same. Okay, for that reason, from right angle triangle EFG, what we need to calculate? Apply sin phi there. Why we are applying sin phi? Because opposite side required for us. That's why sin phi I am applying here. Opposite side is EF. Hypotenuse is I2x02. Observe carefully. Opposite side is EF. Hypotenuse I2x02. So sin phi, opposite side is EF. Hypotenuse I2x02. Now this EF is nothing but BC only. Same magnitude both. Then what is BC? I2x02 sin phi. Therefore BC also we got. Now substitute in the equation. Therefore E2 minus V2 equal to AB is I2 R02 cos phi plus I2 x02 sin phi. Okay. This is the magnitude of voltage drop. This is drop E2 minus V2. But what is regulation? It should be expressed as a no load voltage again. Therefore, regulation is E2 minus V2 by E2. So just divide the complete equation with E2. That's it. I2 R02 divided by E2. Directly I am dividing for both the terms at a time. Cos phi plus I2 X02 divided by E2 sin phi. Okay. This is per unit regulation. This is per unit regulation. Now, what is this value? IR, resistance drop by voltage. This is per unit resistance only, no? This is called per unit resistance. Simply like that, I2X02 is reactance drop, voltage drop divided by voltage. This is per unit reactance. So per unit resistance into cos phi plus per unit reactance into sin phi. This is in per unit. Therefore, if you want percentage regulation, just multiply complete equation with 100. It is converted to percentage or cos phi plus percentage x sin phi. So finally, this is the voltage regulation equation. Okay. Now, in the starting of today's class, I said to find voltage regulation, only short circuit test is enough. Now you can understand what is the reason, because here we have only R and X terms. That percentage or percentage X we can find from short circuit test. Enough. Okay. This is the equation of regulation. So complete up to this today. Tomorrow we continue the same topic. So this is very important, this introduction part. That's why I said you should be present for this introduction, so that tomorrow you can understand very easily. Clear all of you this? So whenever voltage drop increase, regulation also increases. Hello, tell me.
Hello, sir.
Tell me.
Conditions for maximum efficiency, sir. Load current variation.
Which one?
Load current variation, sir.
Efficiency. Slide number.
Slide number. Class. First class, sir. Today.
Hmm.
Conditions for maximum efficiency.
Tell me.
Then, sir, current will be increased and efficiency also increase. Then copper loss is less than iron loss. How, sir?
See, at the maximum efficiency, what is the condition we got? Copper loss equal to iron loss, no?
Uh,
అంటే కాపర్ లాస్ ఏమవుతుంది, కరెంట్ వేరీ అవుతుంది కాబట్టి కాపర్ లాస్ ఆల్సో వేరియింగ్. సో ఈ కండిషన్ మాక్సిమం ఎఫిషియన్సీ దగ్గర బోత్ ఈక్వల్ అయ్యండి. సపోజ్ ఇక్కడ తీసుకో లెస్ దాన్ బిఫోర్ దట్ మాక్సిమం ఎఫిషియన్సీ ఎట్ దిస్ పాయింట్ కరెంట్ ఈజ్ రెడ్యూస్డ్ ఆర్ నాట్? రెడ్యూస్ అయిందంటే కాపర్ లాస్ కూడా రెడ్యూస్ అయింది కదా. సో కాపర్ లాస్ లెస్ దాన్ ఐరన్ లాస్.
Okay. Current will be increased. Now
Then copper loss increases.
Increases. Another doubt, sir. In phasor diagram, sir, normal phasor diagram లో resistor అనేది current కి in phase కదా sir?
Yes. Resistance drop is in phase with current.
In phase in current. RL sir? RL and RC sir?
RL
and RC general గా sir రెసిస్టర్ అనేది కరెంట్ ఏమో ఇన్ ఫేజ్ లో ఉంటుంది.
yes
రియాక్టెన్స్ అండ్ కెపాసిటెన్స్
perpendicular. 90 degrees with resistor current, 90 degrees with current. One is inductor is lagging, capacitor is leading.
Yes sir. అంటే అది కన్ఫ్యూజ్ అవుతుంది సార్. ఇండక్టెన్స్ అనే ఆర్ఎల్ ఉన్నప్పుడు కరెంట్ అనేది వోల్టేజ్ లాగ్ లో ఉంటుంది సార్.
yes RL load kabatti current, overall current is lagging the voltage by some angle whatever they given in the question. So we take an example, some cos 0.8 lag like that.
Okay sir.
Ajay, tell me.
Sir, good evening sir.
Tell me Ajay.
Sir, in general you are said na sir in short circuit test it is only in HV side, but HV side in only 4 to 12% you said na sir, while we are doing
voltage up required is only some 5 to 10%.
Yes sir. But sir you said na sir here in regulation, but it is no load to full load. How it is works sir, but full load means it will create some problem now sir.
Question is not audible clearly.
Sir, you said in short circuit test we cannot apply full load.
Okay
Sir, but here in
short circuit test we are applying full load current only, rated current only flowing na there.
Yes sir.
Why it is flowing? Because load is not connected. In place of that just zero resistance path is connected, short circuit. Because of
yes,
that
sir.
Still rated currents only flowing, but voltage we are not applying rated for that. Small voltage is enough because load is shorted.
Okay sir.
Here currents are same only, no? That's why voltage drop is same in both cases.
Okay sir. Sir, here we are considering full load, directly we are applying load, that is
yes.
That's why we are not considering that problems.
Yes.
Okay sir. Sorry, if we connected this testing LV side, in what will happen sir?
Same loss you will get. Even if you do the same test on LV side, you will get same loss, but LV side if you conduct what is the current on LV side? High current. Then what
yes,
is
sir.
the meter you need to take? High range meter, no?
Yes sir.
That may or may not be available, no?
Yes sir.
High rating. That's why we preferred HV side.
Okay sir. Sir.
Hello sir, good evening sir.
Tell me.
Sir, once open 15F slide sir. 15F. Sir, in second question, what is the maximum efficiency at unity power factor? In second method, cos pi is equal to 1. When unity power factor itself, it is a maximum efficiency, no sir?
Oh yes.
Then why we are finding again X, sir? In second question, directly we place the cos pi is equal to 1. Then I solved like that, sir. But I did
how much
answer.
you got? much?
95.95, sir. 95.96.
What you substituted in that x, what, how much you taken in that
X, I don't take X, sir. I cos pi is equal to 1. Means it cos pi is equal to 1. Itself is
okay.
maximum efficiency.
When maximum efficiency is asked, you have to take two conditions. Both you have to take, not only one condition.
Okay, sir.
Maximum
Sir,
efficiency is possible with two variations. So you have to take both variations, current and power factor, both.
okay, sir. Sir, in 29F, sir. Sir, here voltage regulation of generator is much greater than transformer. Here you wrote 400 by 200, something we denominator reducing. I didn't understand that, sir.
Generally in transformers, this type of voltage ratings we will have 400 by 200 like that. No.
Yes, sir.
What is that voltages? E1, E2, that is. But
Okay.
for generators, whenever there is a voltage on the nameplate, that voltage is always full load voltages, terminal voltages, not EMF in generators.
Okay, sir.
Okay, so that voltage only we take at the denominator to express the voltage regulation of generators. We take at the denominator full load voltage.
Sir, here E means, sir, V, normal V is the 400, that is E1. What is E, sir? Capital E for what, sir?
Capital E will be greater than that, but that is unknown for us. Generator EMF unknown for us. Whatever nameplate voltage is there, that is terminal voltage of generators always.
Sir, okay,
EMF
sir.
they don't give directly.
Yes, sir, we have to find in those generator
That EMF we
problems.
have to find, like a voltage plus drop in that.
Sir, also one doubt, sir. Sir, we always take the multiples of 11 in transformer ratings, 11 kV, 33 kV. Why like that, sir?
That is due to RMS nature of that voltage and current signals. No? So if you find form factor, maybe in networks, the people will tell you all this. Why we are taking 1.1 you will get. So refer one time the form factor for different signals, particularly sinusoidal signal, you will understand why it is.
That only, sir, reason?
Yes, there is no other reason for this.
Okay, sir. Thank you, sir.
Hello, sir.
Tanvi,
Hello, sir. Hello, sir.
tell me, Tanvi.
Sir, my internet got cut, sir. So I had a doubt in the efficiency of this thing, sir. You are taking E2, I2, sir. So I wanted to ask why E2, sir? And you told some reason, but my internet got cut, sir.
Actually, we have to take V2, I2 cos phi.
Yes, sir.
But in a transformer from the data, do you know V2 directly to you?
No, sir.
No. Then how can we substitute that V2? But what we know, E2 we know in place of that. That's why we take approximately there E2 only. And we do calculations. There is no big difference in both. Almost same answers you will get.
Okay, sir. So there's one more doubt in the power transformer and distribution transformer, sir. There was a point saying that in power transformer, copper loss should be kept minimum, sir. So,
yes.
Sir, is in power transformers, sir, is copper loss much greater than the iron loss, sir?
Not much, little greater, because nearly maximum efficiency condition mostly we operate. No, means nearly full load we operate.
Okay.
Full loads. Then full load means definitely copper loss is little greater than iron loss there. But for high rating transformers, definitely as currents rating are very high in kiloamperes, then copper loss is very much greater than iron losses. So for that reason, we need minimum. So that is possible by with a good quality of copper material. So different quality of windings available in market again.
Yes, sir.
Then you have to choose superior quality, good one, so that resistance is less. As much as possible, your loss a little reduce. What?
Thank you, sir. That's all.
Okay. Okay. Charan? Tell me.
నో లోడ్ వర్సెస్ ఫుల్ లోడ్ లో అంటే గ్రేటర్ అని చెప్పారు కదా సార్, నో లోడ్ గ్రేటర్ అని చెప్పారు కదా సార్. అది ప్రతి కేసెస్ లో నో లోడ్ గ్రేటరా సార్?
ఎస్, ఎవ్రీ కేస్. అంటే లీడింగ్ పవర్ ఫ్యాక్టర్ లో చేంజ్ అవుతుంది.
లీడింగ్ పవర్ ఫ్యాక్టర్ లో చేంజ్ అవుతుంది సార్. మరి యూపీఎఫ్ లో 3 కేసెస్ యూజ్ చేయమా సార్?
యూపీఎఫ్ లో ఒకటే పాజిటివ్. ఐ విల్ షో దట్ టుమారో క్లాస్ లో చూపిస్తాను ఎట్లా అనేది.
ఓకే సార్.
Swapnil, Chandrakant.
సార్
Again, Yugashri, tell me.
సార్ అది కేస్ 1 లో ఒకసారి డయాగ్రామ్ మళ్ళీ ఒకసారి ఎక్స్ప్లెయిన్ చేయరా సార్? నాకు అర్థం కాలేదు.
See, first voltage reference, then current is lagging now because lagging power factor we taken. Then resistance drop, reactance drop draw చేయాలి. ఎక్కడి నుంచి డ్రా చేయాలి? వోల్టేజ్ నుంచి డ్రా చేయాలి. వై ఫ్రమ్ వోల్టేజ్? ఇవన్నీ వోల్టేజెసే కదా. వోల్టేజ్ ఇది రెసిస్టెన్స్ డ్రాప్ అన్న వోల్టేజ్, రియాక్టెన్స్ డ్రాప్ అన్న వోల్టేజ్. సో ఫ్రమ్ ద వోల్టేజ్ మనం ఇవన్నీ డ్రా చేయాలి. రెసిస్టెన్స్ డ్రాప్ అనేది ప్యారలల్ టు కరెంట్ and reactance drop perpendicular to current, and the resultant of these three is E2. Now to find the difference E2 minus V2, we are drawing a small radius of semicircle, or arc is drawn so that it will touch this point at D. So manaki AD kavali, AD, but in that CD we cannot find that. That's why we are neglecting that. So AB plus BC only we are calculating. Okay.
There CD why we have to neglecting? CD why we have to neglecting, sir?
Why we are neglecting?
Yes, sir.
Try to calculate చేయి, ట్రై చేయి ఒకసారి. క్యాలిక్యులేట్ చేయగలమా దీన్ని? ఒక రైట్ యాంగిల్ ట్రయాంగిల్ ఇలా ఉంటే మనం ఆ సైడ్స్ తెలిస్తే అదర్ సైడ్ మనం కనుక్కోవచ్చు. అది ఈ రైట్ యాంగిల్ ట్రయాంగిలే కాదు అసలు, ఇట్లా ఉంది కదా ఇది. అండ్ దెన్ హౌ కెన్ యూ ఫైండ్? పాసిబుల్ అయితే ట్రై చేసి నాకు చెప్పాలి.
ఓకే
ఓకే. నెక్స్ట్ చంద్రకాంత్, అనిల్ కుమార్ మల్హోత్రా. హలో చంద్రకాంత్, టెల్ మీ. What? Not audible.
Voltage regulation, sir.
Okay. This one? Which one?
Sir, we are taking the secondary approximate circuit, sir, for calculating voltage regulations.
Because regular voltage, that is load, we are connecting to secondary side only, no?
Okay, sir.
That's why we consider total circuit referred to secondary side.
Okay, sir.
Okay.
Next slide, sir, 29.
Sir,
in this we have explained generator. We are taking a thermal voltage. A transformer also we are taking a no load voltage. So the difference I did not get it, sir.
Because in transformer, which voltage you know? E2 you know or V2 you know? E2 we know.
E2, sir.
That's why this difference we are expressing as a known voltage. But in generators, which voltage will be there on the nameplate? Terminal voltage. Then that voltage we use to express that difference. Okay.
Yes, sir. Sir, in phasor diagram, sir. Sir, in phasor diagram, we are taking a angle approximately, sir, I2 R02, sir.
This angle phi, no?
Yes, sir.
Taking
a right angle triangle, we are taking approximately, sir.
Not approximate, exact 5 only it is, because I2 R02 we are drawing exactly parallel to I2, no? Same angle you will create here.
Okay, sir. Sir, then E2, sir. Sir, from angle of FEG, sir.
FEG, this is phi because observe from I2 R02, this is angle phi, no?
Yes, sir.
Now observe angle phi is the angle between this dotted line and this line. Okay.
Yes, sir.
Now same observe, to this dotted line, this red dotted line is perpendicular.
Yes, sir.
To this I2 R02, this line is perpendicular.
Yes, sir.
And perpendiculars of two perpendiculars again will create same angle or not?
Yes, sir. Okay, sir.
That is also same angle you will get.
Okay. Sir, in 5F, sir, slide number 5F. Sir, can you please explain this? I did not get the maximum efficiency.
No, at maximum efficiency, this is the condition we got. First one, x square I2 square R02 equal to iron loss. X square I2 square R02 means what? Copper loss.
Copper
At some
loss.
load, not at full load, that is. X we don't know, no. At some load it is. And where it is maximum is that x we need to calculate using this equation.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Swapnil, Chandrakant, Teja, Siddharth.
Hello, sir.
Tell me, Siddharth.
Sir, can you explain the significance of per unit system, sir? Why we are using per unit? Hello.
With the per unit calculations, the calculation will become little easy now, because we no need to take big numericals. Just in per unit 0.51 like that we take.
Can you give one example, sir? Any like
suppose the efficiency we are using.
Yes.
See. Suppose there is a 10 kVA transformer of some voltage rating and all, and iron loss is given in some watts and copper loss also given in some watts.
Yes.
Then all you need to substitute to find efficiency at some different fraction of loads.
Yes.
3/4 full load.
Yes.
You need to substitute x volt ampere, the big values.
Yes, sir.
But if it is in per unit, no, I will take 10 kVA means 1 per unit.
Okay, okay. Only for
calculation will become simple. No need to take 10 like big values.
Okay. Okay, thank you.
Hello, sir. I am audible.
Chandrakant, tell me.
हाँ यस सर एक्चुअली मुझे क्रॉस सेक्शन एरिया जो होता है ना हमारा ट्रांसफार्मर का मतलब कोर का उसमें डाउट था। मतलब हम टोराइडल कॉइल लेते हैं ना उसमें हम पायर स्क्वायर उसका क्रॉस सेक्शनल लेते हैं, लेकिन हम जो स्क्वायर कोर होता है तो उसमें साइड स्क्वायर लेते हैं। तो उसमें साइड स्क्वायर में सर टोटल एरिया मतलब आ जाता है ना, तो फिर हॉलो एरिया भी उसमें इंक्लूड क्यों करते हैं हम?
वेट।
हाँ सर।
जब ये स्क्वायर कोर है ना,
हाँ सर,
इसमें हम ऐसा एरिया नहीं लेते, टोटल एरिया नहीं लेते हैं, इसमें भी क्रॉस सेक्शन ही लेते हैं ना।
हाँ मतलब सर लेकिन हम उसका साइड स्क्वायर लेते हैं ना फिर।
साइड स्क्वायर ही है, मगर इस इधर क्या लेना चाहिए मींस यू हैव टू टेक कंप्लीटली लिम्ब, एक लिम्ब को ले लेना इधर। सो डोंट टेक कंप्लीट स्क्वायर, टेक वन लिम्ब। ये लिम्ब का क्रॉस सेक्शन भी स्क्वायर ही है ना।
हाँ
उसे
तो
हम कैलकुलेट करते हैं।
ओके तो फिर सर एप्रोप्रिएट एरिया तो नहीं आएगा ना उससे, फिर साइड स्क्वायर करेंगे तो
साइड स्क्वायर
तो मतलब हाँ मतलब जनरलाइज एरिया हम निकालते हैं क्या, मतलब अप्रोक्सीमेट?
दैट एरिया इन द इक्वेशन क्या है, कभी भी वो क्रॉस सेक्शनल एरिया ही है ना, नॉट कंप्लीट कोर एरिया। सो जब हम ये सर्कुलर टोरॉइडल कोर में जो एरिया कैलकुलेट करते हैं ये भी क्या है, क्रॉस सेक्शन ही है, पाई आर स्क्वायर। हम इसे टोटल नहीं लेते हैं ना, टोटल क्या लेते हैं, लेंथ, मीन लेंथ कैलकुलेट करते हैं 2 पाई आर सर्कमफ्रेंस।
हाँ सर टोरॉइडल का मुझे समझ में आया, लेकिन
ये भी वही है, ये भी सेम टोटल एरिया हम कैलकुलेट नहीं करते हैं, ये क्रॉस सेक्शन का ही कैलकुलेट करते हैं।
ओके लेकिन पर सर मुझे समझ नहीं आया कि हम साइड स्क्वायर लेंगे तो यार तो टोटल आ जाएगा ना वो फिर।
तो ये साइड मींस ना, ये साइड, ये क्रॉस सेक्शन का साइड है, उसे हम कैलकुलेट करते हैं।
मतलब ए जो दिया हमें जो साइड दिया होता है तो वो उसका साइड दिया होता है ना कि टोटल का दिया होता है?
नहीं, वो भी स्क्वायर कोर का मतलब वो उसमें क्वेश्चन में जो दिया है ना, स्क्वायर कोर का क्रॉस साइड है, वो क्रॉस सेक्शन का साइड ही है, नॉट कंप्लीट कोर।
ओके मतलब क्रॉस सेक्शन का। ओके ठीक है फिर सर वही समझ। थैंक यू।
आप ये समझता है कि बीच में सब हॉलो एरिया है ना, ये सब आ जाएगा उसमें।
हाँ मुझे लगा कि ओबी एरिया इसमें आ जाएगा, तो वो कैसे हम ले रहे हैं?
नहीं वही नहीं, क्रॉस सेक्शन।
ओके सर थैंक यू सो मच।
तेजा।
हेलो सर।
टेल मी तेजा।
సార్ ఎఫిషియన్సీ కర్వ్లో అప్ టు కాపర్ మ్యాక్సిమం ఎఫిషియన్సీ వరకు లీనియారిటీ ఫాలో అవుతుంది కదా సార్. ఆ తర్వాత డీకే ఎందుకు ఫాలో అవుతుంది సార్? తర్వాత సేమ్ లీనియర్టీ ఫాలో అవ్వాలి కదా సార్? ఎఫిషియన్సీ కర్వ్ సార్.
అంటే మనకి వేరియేషన్ మాక్సిమం ఎట్ వన్ కండిషన్ లో వస్తుంది కదా, ఆ తర్వాత ఏమవ్వాలి? సో అకార్డింగ్ టు మన వేరియేషన్ కరెంట్ ఇంక్రీజ్ అవుతుంది కాబట్టి లాస్ ఇంక్రీజ్ అవుతుంది, ఎఫిషియన్సీ తగ్గాలి కదా.
అవును సార్. అవును సార్.
సో అందుకే అది
Yes,
అట్లా
sir.
వేరీ అవుతుంది, నాట్ లీనియర్. లీనియర్ గా రాదు.
ఓకే సార్. ఓకే సార్. ఓకే సార్.
ఓకే
థ్యాంక్ యూ సార్.
మొహమ్మద్.
Sir. Sir.
बताना.
Sir, this primary power factor means angle between V1I1 or E1I1, sir. You should consider for problems.
Actually V1I1 or E1I1 also you can take because almost both are same. Generally
Sir,
load,
I have
load.
a small, I need a small clarification. Sir, please draw that primary circuit, sir. Refer to primary. Whole circuit, refer to primary.
R01, X01.
Sir, here where do we indicate E1, sir? No
Where?
need of no load branch, sir. No need of no
remove
load.
this. Okay, remove this.
V1 I know, I1 I know, but where do we represent that E1, sir? E1 or E2 dash?
V1 or?
E1, sir. E1 or E2 dash, where we represent it, sir?
So here you cannot represent because actually E1 is only for R1 X1 drop. Now after R1 X1 E1 should be there, but R01 totally we combined here.
Sir, okay, sir. Split it, sir.
Then here you can represent E1.
Okay. Now, if in case we can apply KVL and KCL equations to this circuit and solve, sir.
In tomorrow's class, I will show some this voltage regulation while calculating how to refer primary, secondary, and what it exactly means. So tomorrow I will show you some circuits.
Okay, sir. The second case of efficiency, sir, load versus power factor variation. Sir, in that you've drawn graph, sir. Sir, with x-axis, y-axis, what are there? Sir? Load and
efficiency and current load magnitude only,
but
different loads we are taking. Same current with a different power factor. Then with the same current, if you find efficiency is highest for UPF. If you want maximum efficiency, then both conditions you should apply. Okay.
Sir, 1 second. This, sir. Sir, this power transfer and distribution transformer, you have discussed points, sir. Sir, in that the maximum efficiency occurs at dash percent of load for power and distribution. There's a question like that, no?
Maximum efficiency occurs for power transformer near to full load.
Near full load. Okay, sir.
Full load.
Then,
but for distribution, approximately some 82 or 70 to 85% like that.
72.
Okay. Or 80 to 90, it will change from books to books. 80 to 90% or 70 to 80%, some books like that. Not at full load, nearly that range, 70 to 90 approximately.
Okay, sir. Thank you. Sir, this one, sir. The trigonometer we have taken V for the in voltage regulation formula. We have taken V for generator and E2 for transformer. We have said the reason that they'll indicate the full load voltage for generator and no load voltage for transformer. That's sir. Sir, that don't seems to be related to that point, sir.
Then which one?
I mean, why? मतलब वो clarity नहीं आ रहा sir. भाई वैसा रहता अपन ले लेते क्या denominator में?
Because in transformer, what voltage always you know, E1 or E2 only na we know. Do you know about terminal voltages in transformer? They never indicate on the nameplate. Then how can we substitute this one? Because you don't know that what load they are connecting first.
Sir, we can find and substitute now, sir. If
how can you find? First of all, you don't know load. Then how can you find V2?
Okay. Okay, sir.
Okay.
Thank you, sir.
Hello, sir.
Tell Nilesh.
Hello,
Hello,
sir.
sir.
Tell me, Nilesh.
Hello. Sir, in open circuit test, वो शॉर्ट सर्किट टेस्ट में वो पावर ड्रॉन बाय ट्रांसफार्मर हम इक्वल टू लॉसेस लेते हैं ना?
यस.
तो उसमें वो कॉपर लॉसेस प्लस आयरन लॉस होता है, उसमें आयरन लॉस बहुत ही स्मॉल है सर. वो स्मॉल कैसे है मतलब?
ओसी टेस्ट में जो भी पावर ड्रॉ कर रहा है ट्रांसफार्मर वो क्या है, ऑलमोस्ट आयरन लॉस है. बिकॉज टोटल वाट मीटर जो भी मेजर कर रहा है ना W0 वो क्या है, लॉसेस क्या होते हैं जनरली, आयरन लॉस प्लस कॉपर लॉस. मगर ओसी टेस्ट में कितना करंट फ्लो कर रहा है, स्मॉल करंट है ना.
यस सर.
उसके वजह से कितना कॉपर लॉस आएगा, I0 स्क्वायर R1 ही आएगा. वो तो नेग्लिजिबल है ना.
सर सेम कंडीशन इन शॉर्ट सर्किट टेस्ट देयर इज अ स्मॉल आयरन लॉस. हाउ
इन शॉर्ट सर्किट टेस्ट वाट मीटर रीडिंग जो भी मेजर कर रहा है, क्या मेजर कर रहा है, लॉसेस. अगेन वो लॉसेस क्या है, आयरन लॉस प्लस कॉपर लॉस. मगर शॉर्ट सर्किट टेस्ट में रेटेड करंट तो जा रहा है ना वाइंडिंग्स में.
ओके,
टोटल कॉपर लॉस आ जाएगा, बट मगर आयरन लॉस स्मॉल आएगा. क्यों आएगा, कितना वोल्टेज अप्लाई कर रहा है ये टेस्ट में, स्मॉल वोल्टेज अप्लाई कर रहा है.
ओके ओके सर.
देन आयरन लॉस इज नेग्लिजिबल.
Okay, sir. Sir, in loaded condition of transformer, usually we neglect I0, sir. Why? मतलब उसकी वैल्यू कम होती है क्या always?
यस, लोडेड कंडीशन में I0 का परसेंटेज वेरी स्मॉल ना, 5% फुल लोड से, सो इसलिए इसे नेग्लेक्ट करते हैं.
तो हम ऑलवेज सेकंड केस का अप्रोक्सीमेशन सर्किट रिप्रेजेंट करते हैं ना.
यस यस, लोड केस में.
ओके सर. ओके सर, थैंक यू, दैट्स इट.
Sirisha.
Sir, can you please explain load power factor variation?
Load power factor?
Load power factors variation, sir.
Ante lagging, leading, lagging power factor, UPF.
Lagging, sir.
Figure?
Yes, sir.
Okay. Doubt?
సార్ రెగ్యులేషన్ నార్మల్ రెగ్యులేషన్ అనేది ఎందుకు వచ్చింది సార్, ఆ పాయింట్ నాకు ఎగ్జాక్ట్ గా అర్థం కాలేదు.
అంటే మనం ఎప్పుడైతే లోడ్ కనెక్ట్ చేస్తామో ట్రాన్స్ఫార్మర్ వోల్టేజెస్ ఈఎంఎఫ్ ఇండ్యూస్ అయ్యి 200 అయితే మనకి లోడ్కి వచ్చేది తగ్గిపోతుంది.
ఓకే సార్.
ఎందుకు తగ్గుతుంది, బికాజ్ ఆఫ్ వైండింగ్ లో రెసిస్టెన్స్ రియాక్టెన్స్ డ్రాప్ అవుతాయి కదా వోల్టేజెస్.
ఎస్ సార్.
సో ఎంత డ్రాప్ అయింది మనకి తెలియాలి కదా.
ఎస్ సార్.
సో అదే మనం వోల్టేజ్ రెగ్యులేషన్ అంటున్నాం దాన్ని, ఆ క్యాలిక్యులేషన్.
ఓకే ఓకే సార్.
అది ఎక్కువ డ్రాప్ అయితే మనకు వచ్చే వోల్టేజ్ తగ్గిపోతుంది.
ఓకే ఓకే సార్, థ్యాంక్ యూ సార్.
వోల్టేజ్ రెగ్యులేషన్ తక్కువ ఉండాలి.
ఓకే సార్.
భాస్కర్.
హలో సార్.
టెల్ భాస్కర్.
సార్ ఈ వోల్టేజ్ రెగ్యులేషన్ లో సెకండ్ పాయింట్ చెప్పారు కదా సార్, అది ఎట్ ఎనీ లోడ్ అని, ఆ పాయింట్ ఒకసారి చెప్పండి సార్.
మనం డెఫినేషన్ లో ఏం చెప్పాము, వోల్టేజ్ రెగ్యులేషన్ ఈజ్ రేషియో ఆఫ్ చేంజ్ ఇన్ వోల్టేజ్ ఫ్రమ్ నో లోడ్ టు ఫుల్ లోడ్ అన్నాం. కానీ మనం ఆల్వేస్ ఫుల్ లోడే కనెక్ట్ చేస్తామా ట్రాన్స్ఫార్మర్ కి, ఏ లోడ్ అయినా కనెక్ట్ చేయొచ్చు కదా.
ఎస్ సార్.
సో అందుకే జస్ట్ ఐ గివెన్ ఎట్ ఎనీ లోడ్.
ఓకే సార్. సార్ ఇది డిఫరెంట్, ఈ పవర్ ట్రాన్స్ఫార్మర్ డిస్ట్రిబ్యూషన్ ట్రాన్స్ఫార్మర్ డిఫరెంట్ చెప్పారు కదా సార్. అక్కడ కాపర్ లాస్, ఇందులో డిస్ట్రిబ్యూషన్ ట్రాన్స్ఫార్మర్ లో ఐరన్ లాస్ ఎందుకు తీసుకున్నారు సార్, అది పాయింట్ అర్థం కదా. 22
డిస్ట్రిబ్యూషన్ ట్రాన్స్ఫార్మర్ లో మనకి లోడ్ అనేది ఆల్వేస్ ఉంటుందా సేమ్ లోడ్ ట్రాన్స్ఫార్మర్ మీద? నో,
లేదు సార్.
కానీ ట్రాన్స్ఫార్మర్ కి సప్లై ఉంటుందా లేదా ప్రైమరీ సైడ్?
ఎస్ సార్.
అంటే వోల్టేజ్ ఆల్రెడీ అప్లై అయింది కదా ఆల్వేస్. అంటే ఐరన్ లాస్ డిపెండ్స్ ఆన్ వోల్టేజ్, అది 24 hours ఉంటుంది.
ఓకే సార్.
కానీ కాపర్ లాస్ అలా ఉండదు కదా.
అవును సార్.
అందుకే మనం ఐరన్ లాస్ ని కంట్రోల్ చేయాలి డిస్ట్రిబ్యూషన్ ట్రాన్స్ఫార్మర్స్ లో. కానీ పవర్ ట్రాన్స్ఫార్మర్స్ లో రెండు ఉంటాయి, కానీ ఏ లాస్ ఎక్కువ ఉంటుంది, కాపర్ లాస్ జనరల్లీ గ్రేటర్. అందుకే దాన్ని కంట్రోల్ చేయాలి.
గ్రేటర్ అని ఎట్లా చెప్తాం సార్ అందులో?
జనరల్లీ మనం ఫుల్ లోడ్ దగ్గర ఆపరేట్ చేస్తాం కదా పవర్ ట్రాన్స్ఫార్మర్స్ ని.
సరే సార్. ఓకే.
అంటే ఫుల్ లోడ్ దగ్గర నియర్లీ మనకి ఆల్వేస్ కాపర్ లాస్ గ్రేటర్ దెన్ ఐరన్ లాస్.
ఓకే సార్.
this I'm closing for today. Tomorrow we meet at same time. Good night.